Think for a moment about the world you wake up to every single day. The gentle hum of a smartphone buzzing on the nightstand, the instant warmth of a microwave heating your breakfast, the precise directions from a satellite guiding your car. We live in an age of technological miracles, surrounded by comforts so seamless we barely notice them. It's easy to feel that human progress is a straight, upward line, that our modern era stands alone at the pinnacle of innovation. But what if that entire picture is wrong? What if the spark of genius that illuminates our 21st century is not a new flame, but an ancient one, rediscovered? This is the profound and humbling mystery we are about to explore. We are going on a journey back through the corridors of time, to an age without electricity, without mass production, without the scientific method as we know it. And there, in the dust and shadows, we will find something astonishing. We will uncover objects and ideas of such breathtaking sophistication, such elegant complexity, that they seem to have fallen out of time itself. These are the ancient inventions that were centuries, even millennia, ahead of their time. They are monuments to a forgotten brilliance, created by minds that saw the world with a clarity we are only now beginning to reclaim. Prepare to have everything you thought you knew about history challenged. This is not a story of primitive tools and simple beginnings. This is a story of lost genius, of civilizations that reached intellectual heights that would not be scaled again for over 1,000 years. We will witness intricate mechanical computers that could predict the movements of the stars, revolutionary surgical tools that understood the principles of sterilization long before germ theory, and engineering marvels that stand defiantly against the elements to this very day. These creations whisper a tantalizing secret across the centuries, that human potential is not bound by its era. So join me as we peel back the layers of time to reveal 30 incredible achievements. We will trace the echoes of this lost knowledge, follow the threads of inspiration that were broken and then miraculously rejoined, and rediscover the awe-inspiring truth that the ancient world was far more advanced than we ever imagined. Our journey into the realm of lost technology begins not in a library or a temple, but at the bottom of the sea. In the year 1900, off the coast of the tiny Greek island of Antikythera, sponge divers made a stunning discovery: the wreck of a Roman-era cargo ship, its hull filled with marble statues and other treasures. But among these classical artworks, one object stood out as utterly bizarre. It was a lump of corroded bronze and wood, so encrusted with 2,000 years of sea life that its true nature was completely hidden. Initially set aside as a curiosity, this unassuming lump would later be recognized as the single most important scientific artifact ever recovered from the ancient world. Years after its discovery, as museum conservators began to carefully clean the object, the truth started to emerge. They found intricately cut bronze gears, precisely aligned and mounted within a wooden frame. Inscriptions, tiny and densely packed, spelled out instructions and celestial information. This was not a statue or a piece of jewelry. It was a machine. Dubbed the Antikythera Mechanism, this device is now understood to be the world's oldest known analog computer. Its purpose was nothing short of magnificent: to predict the complex dance of the heavens. By turning a hand crank on the side, an ancient user could calculate the future positions of the sun, the moon, and the 5 planets known to the Greeks. It could forecast lunar and solar eclipses, and even account for the irregular orbit of the moon. It was, in essence, a mechanical model of the entire known universe, small enough to be housed in a wooden box about the size of a shoebox. The sophistication of its engineering is what truly defies belief. The device utilized a system of at least 30 interlocking bronze gears, including a remarkably complex differential gear, a component whose invention was previously credited to the automobile industry of the 19th century. This assembly of gears created a clockwork universe where the turns of the crank precisely mirrored the celestial cycles. One gear represented the sun's yearly journey, another the moon's monthly orbit, and yet others the slow precession of the planets. The mechanism didn't just show where a planet would be, it showed the entire system working in harmony, a miniature orrery of breathtaking precision. To put this achievement into perspective, consider the technological landscape that followed. For over 1,000 years after the Antikythera Mechanism was lost at sea, nothing of comparable mechanical complexity would appear in the historical record. The scientific knowledge required to design it, the metallurgical skill to craft its tiny, perfect teeth, and the philosophical understanding of a mathematical universe, all of this vanished with the fall of the Hellenistic world. It stands as a lonely beacon of a potential technological path not taken, a secret masterpiece of Greek engineering that whispers to us from a past far more insightful than we had ever dared to dream. From the cool, calculated mechanics of the Antikythera device, we now turn to an invention born of sheer desperation and war, a weapon so terrifying it seemed to harness the very fires of hell itself. While the ancient Greeks modeled the heavens, their successors, the Byzantine Empire, created something to turn the seas into an inferno. This was Greek fire, a technological marvel whose secret was guarded so fiercely that it eventually vanished from history, leaving behind only legends of its devastating power. Picture the scene: Constantinople, the magnificent capital of the Byzantine Empire, is surrounded. A massive Arab fleet, representing the rising power of the Umayyad Caliphate, blocks the city's harbors. It is the 7th century, and the survival of Christendom in the East hangs by a thread. The Byzantines are outnumbered and facing annihilation, but as the enemy's ships close in for the final assault, something unprecedented happens. Byzantine Draman warships advance, and from their prows, not arrows or stones, but jets of liquid fire shoot forth. This is no ordinary flame. It clings to everything it touches: wooden hulls, sails, and most chillingly, the water itself. The sea begins to burn. Panicked sailors leap into flames that float on the waves, and the attacking fleet is consumed in an unstoppable blaze. This was not just a victory, it was a psychological earthquake. The Arabs, who left their own accounts of the battles, spoke of a fire that was summoned by sorcery, a weapon against which there was no defense. The genius of Greek fire, known to the Byzantines as sea fire or liquid fire, lay in its mysterious formula. Its exact composition was a state secret on par with modern nuclear codes, known only to a handful of individuals, reportedly even the emperors themselves. Historical analysis suggests it was a complex mixture based on naphtha, a light form of crude oil, which would explain its ability to float and burn on water. But the true secret ingredient was likely a chemical trigger that caused it to ignite upon contact with water. Many historians and chemists believe quicklime, a substance that reacts violently with water to generate intense heat, was a key component, perhaps allowing the mixture to ignite as it was pumped through the siphons. The delivery system was as advanced as the weapon itself. It was not thrown in pots. It was pressurized and expelled through bronze tubes mounted on the prows of ships, creating a continuous stream of fire that could be aimed like a primitive flamethrower. Some accounts even describe handheld versions, known as cherisiphons, for use by soldiers on land. The most astounding aspect of Greek fire is that its secret died with the Byzantine Empire. As the empire slowly crumbled over the centuries, the precise formula and the engineering knowledge for the pressurized siphons were lost. Countless attempts have been made to reverse engineer it, but no modern reproduction has ever perfectly matched the descriptions from historical accounts, particularly its signature trait of being nearly impossible to extinguish, with water only seeming to spread the blaze. It remains one of history's greatest unsolved chemical puzzles. For 7 centuries, this weapon was a primary reason for Byzantine naval dominance, a technological advantage that protected an empire against overwhelming odds. Its disappearance is a stark reminder that progress is not always a one-way street. Sometimes, brilliant lights are simply snuffed out, leaving behind only the echo of their fearsome glory. But if Greek fire represents a terrifying technology that was tragically lost, our next invention presents the opposite scenario: a miraculous material whose secret was not lost, but simply ignored, hiding in plain sight for centuries. While the Byzantines mastered destruction, the ancient Romans perfected creation on a monumental scale. Their legacy is written not in flames, but in stone and mortar, and to understand its genius, we need only look at a building that has defied time, weather, and even earthquakes for nearly 2,000 years: the Pantheon in Rome. This magnificent temple, with its vast, unsupported dome, a record it held for over 13 centuries, is not just an architectural wonder. It is a silent rebuke to our own modern infrastructure. In an age where many of our concrete structures are engineered to last 50 or 100 years before showing significant decay, the Pantheon stands perfectly intact, a flawless shell that has sheltered generations. The question is not just how they built it, but why our own concrete, for all our advanced science, seems to crumble so much faster. The answer lies in a simple but profound chemical secret, one the Romans discovered largely by accident. The key ingredient is a specific type of volcanic ash, known as pozzolana, found in abundance around the Bay of Naples near the city of Pozzuoli. When the Romans mixed this fine, sandy ash with lime and seawater, they triggered a chemical chain reaction far more complex and durable than the process that creates modern Portland cement. Our concrete primarily hardens through a reaction with water that forms a crystal structure, but this structure can be brittle and is vulnerable to cracks, which then allow water to seep in, freeze, and expand, causing further damage. It's a slow but inevitable cycle of decay. Roman concrete, however, did something extraordinary. The combination of lime and the silica-rich volcanic ash created a calcium-aluminum silicate hydrate gel. This might sound technical, but its effect is simple. It acts as a kind of self-healing agent. Imagine the microscopic structure of Roman concrete not as a rigid, static framework, but as a living, dynamic material. When tiny cracks begin to form over centuries, exposure to rainwater or groundwater actually kicks off a new chemical reaction. The water dissolves some of the remaining lime and volcanic ash particles, which then travel into the fissures and slowly precipitate, effectively gluing the crack back together from the inside. This is the complete opposite of modern concrete, where water is the primary agent of destruction. This self-healing property explains the mind-boggling durability of Roman marine structures, like the harbor at Caesarea in modern-day Israel. Breakwaters and piers submerged in the corrosive Mediterranean seawater for 2 millennia are not just still standing. They have actually grown stronger, as the constant water flow has facilitated ongoing chemical reactions that have solidified the concrete into a rock-like mass. For a long time, modern engineers dismissed Roman concrete as a primitive, lost art, assuming our technology was superior in every way. It's only in recent decades, as our own infrastructure faces alarming rates of deterioration, that scientists have turned to the ancients for answers. Using advanced tools like electron microscopes and X-ray microdiffraction, they have been able to analyze samples of Roman concrete at a molecular level, finally decoding the precise recipe and the stunningly long-term chemical processes at work. The discovery is humbling. The Romans, without any knowledge of modern chemistry, had engineered a material that was not only strong but inherently sustainable and resilient. They used materials locally available to them, and the process itself actually absorbs carbon dioxide from the air over time, making it a potential model for greener construction today. The lesson of Roman concrete is perhaps the most profound of all. It isn't a story of a lost secret, but of a disregarded one. The knowledge was never truly lost. The recipe was described by architects like Vitruvius. The real loss was a shift in priorities. The Romans built for eternity, investing in projects meant to echo through the ages. Our modern world, for all its benefits, often prioritizes speed and cost efficiency over longevity. Now, as we face the colossal cost of repairing and replacing our crumbling bridges, roads, and buildings, we are finally looking back to this ancient wisdom, not with condescension, but with a newfound respect. We are beginning to understand that the true genius of Roman concrete wasn't just in its composition, but in its philosophy, a commitment to building a world that would last. Moving from the monumental scale of Roman architecture, we encounter an object so small and unassuming that its true purpose remains one of archaeology's most tantalizing puzzles. In the 1930s, during excavations of a 2,000-year-old Parthian village near Baghdad, workers uncovered a series of peculiar items. They found a simple clay jar, about the size of a man's fist. Inside it was a carefully rolled copper cylinder, sealed at the bottom with a sheet of copper, and within that cylinder was an iron rod. The rod was held firmly in place by an asphalt plug, which insulated it from the copper cylinder. creating a clear separation between the two different metals. To the untrained eye, it looked like a sealed container for a sacred scroll or a simple storage vessel. But to German archaeologist Wilhelm Koenig, who studied the find, the arrangement looked uncannily like something else entirely, an electric cell. The theory Koenig proposed was as revolutionary as it was controversial. He suggested that if this jar were filled with an acidic liquid, something as common as vinegar or grape juice, the combination would create a chemical reaction. The acidic fluid would act as an electrolyte, interacting with the two different metals. The iron rod would corrode, releasing electrons, while the copper cylinder would collect them. By connecting a wire or a metal object between the iron and the copper, a small but measurable electric current would flow. In essence, this humble clay pot could have been a primitive battery, predating the official invention of the voltaic pile by Alessandro Volta in the year 1800 by more than a millennium. What possible use could an ancient civilization have for such a faint trickle of electricity? The most compelling hypothesis involves not powering devices, but adorning them. The theory suggests these Baghdad batteries could have been used for electroplating, the process of using an electric current to bond a thin layer of a precious metal, like gold, onto the surface of a less valuable one, like silver. There are numerous artifacts from the same region and era, particularly small silver objects intricately plated with a fine, even layer of gold. While artisans of the time had other methods for gilding, such as mercury-based fire gilding, electroplating would have produced a strikingly smooth and consistent finish with remarkable efficiency. A craftsman could have connected several of these jars together to create a stronger current, dipped the silver object into a gold salt solution, and achieved a result that would have seemed almost magical. Yet, this captivating idea is met with fierce skepticism from many in the academic community. The primary objection is the complete lack of any corroborating evidence. No wires have been found with the jars. No ancient texts describe anything resembling electrical phenomena or electroplating. There is no depiction of such a process in any artwork. Furthermore, the asphalt plug, which is so crucial to the battery theory as an insulator, could have had a much more mundane purpose, simply being an effective seal to keep the contents of a scroll container safe from moisture. Critics argue that if these were truly batteries, we would expect to find a wider distribution of them, or some other artifact that clearly relied on their use. Without that, the theory remains an intriguing but unproven what if. The debate surrounding the Baghdad Battery is a perfect example of the challenges in interpreting the ancient world. Is it a case of modern minds projecting our understanding of science onto an object that had a completely different, more ordinary function? Or have we stumbled upon a genuine fragment of forgotten knowledge, a spark of empirical discovery that was either lost or never fully developed? The truth may never be known for certain, but the object's very existence forces us to consider the boundaries of ancient innovation. It stands as a quiet, enigmatic reminder that the past may hold secrets we have not even begun to suspect, and that the line between myth and history is sometimes as thin as a wire connecting two ancient metals. From the mysterious electrical potential of the Baghdad jars, we now turn our attention to an artifact that challenges our understanding of ancient perception itself. In the ruins of the ancient Assyrian palace of Nimrud, modern-day Iraq, archaeologists uncovered a small, unassuming piece of rock crystal dating back over 3,000 years. It was ground into a distinct oval shape, with one flat face and one gently convex face, and it possessed a property that was nothing short of remarkable. It could bend light. This is the Nimrud lens, and its existence poses a fascinating question. Were the Assyrians, a civilization renowned for their conquests and colossal stone carvings, also pioneering the science of optics? The lens itself is a masterpiece of early craftsmanship. Made from natural rock crystal, it measures roughly 1.5 inches across and has a focal point about 4.5 inches from its surface. While it's not optically perfect by modern standards, its ability to magnify objects is undeniable. If you were to hold it over a piece of cuneiform text on a clay tablet, the intricate wedge-shaped characters would appear larger and clearer. This has led to the most widely accepted theory. that it was used as a simple magnifying glass by Assyrian artisans or scribes. Imagine an elderly craftsman, his eyes strained from years of intricate work, using this crystal to examine the finest details of a jewelry piece or to correct the tiny errors on an important royal inscription. It's a practical, logical explanation that fits neatly into our understanding of the ancient world. However, another compelling possibility exists. The lens could have served as a burning glass. If focused precisely on a point under the intense Middle Eastern sun, the crystal would concentrate the sun's rays, generating enough heat to smolder tinder and start a fire. This would have been a tool of immense practical and perhaps even ceremonial value. The ability to summon flame from the sun itself would have seemed like a form of magic, a power worthy of a king or a high priest. The Assyrians were deeply interested in astronomy and celestial omens, so a device that literally captured the power of the sun would have held profound significance beyond its mundane utility. But the most tantalizing and controversial theory pushes the boundaries of what we believe possible. The renowned Italian astronomer Giovanni Patinolo has suggested that the Nimrod lens, mounted in a simple frame, could have been the key component of a primitive telescope. Assyrian astronomers were meticulous observers of the night sky, charting the movements of planets and stars for both religious and calendrical purposes. Could they have used such a lens to enhance their vision? Even a weak telescope would have allowed them to see the moons of Jupiter or the phases of Venus, discoveries that history credits to Galileo nearly 2.5 millennia later. While no other lenses or mounting apparatus have been found to support this idea, it forces us to wonder if the Assyrians were on the cusp of an optical revolution that was lost amidst the sands of time and the fall of their empire. The Nimrod lens remains a quiet, crystalline enigma, a simple object that reflects not just light, but the brilliant and perhaps far-seeing curiosity of the ancient mind. Yet, for all the ingenuity of the Assyrian lens, our next discovery presents a puzzle not of science, but of language, a message sent to us from the heart of a lost civilization, waiting silently for over 3 millennia to be read. Deep within a basement storeroom of the ancient Menon Palace of Phaistos on the Greek island of Crete, Italian archaeologist Luigi Pernier made a find in 1908 that was as beautiful as it was baffling. It was a small, fired clay disc, roughly the size of a standard dinner plate, but this was no simple piece of pottery. Its entire surface, front and back, was covered with a continuous spiral of mysterious, finely crafted symbols. There were human figures and animals, men with feathered headdresses, ships, shields, and bees, along with a host of abstract shapes. These symbols were not carved or painted. Astonishingly, they had been stamped into the soft clay with individual seals, each character a separate piece of type, making the Phaistos disc the world's oldest known example of movable type printing. This single fact is what elevates the disc from a curious artifact to a historical thunderclap. The technology it represents, creating a reusable set of characters to impress words onto a medium, would not be reinvented until Johannes Gutenberg developed his printing press in the 15th century, a gap of more than 3,000 years. The Minoans, a sophisticated Bronze Age culture known for their sprawling palace complexes and vibrant frescoes, had stumbled upon a revolutionary idea for disseminating information. But here the mystery deepens, because we have no other examples of this technology from the Minoan world. No other stamped texts, no discarded typesets, no clay tablets bearing the same imprinted symbols. The Phaistos disc is a complete anomaly, a lone beacon of a concept that, for reasons we can only guess, was either abandoned immediately or whose other manifestations have been lost to time. Naturally, the central question is, what does it say? For over a century, the world's best linguists, archaeologists, and amateur code breakers have tried to crack its code, and all have failed. The disc features 241 tokens, comprised of 45 distinct signs. This suggests it represents a syllabic script, where each symbol stands for a syllable like ka, or tu, rather than an alphabet or a purely pictorial language. The text is neatly divided into sections by incised lines, almost like paragraphs, and the spiral direction on one side is clockwise, and counterclockwise on the other, adding to the complexity. The failures to decipher it are as numerous as they are imaginative. Some theorists propose it is a religious hymn, a prayer to a Minnow goddess. Others argue it is a narrative, perhaps a story of a king's great deeds or a record of a significant historical event. More fanciful suggestions have included a geodetic document, an ancient board game, or even an astronomical calendar. The fundamental problem is that the disk is what linguists call an isolated corpus. It is the only known example of this specific script. Without a bilingual text, a Rosetta Stone, for the Phaistos disk, or any other examples to compare it against, decipherment is virtually impossible. We have no starting point, no known language to map the symbols onto. Is it an early form of Greek, a unique Minoan language lost when their civilization was conquered? Or could it be a foreign document, brought to Crete from another culture across the sea? Each theory is built on sand, lacking the corroborating evidence needed to hold it firm. The very purpose of the disk remains elusive. Was it a royal proclamation meant to be displayed, a sacred object for a temple? Or was it, perhaps, an early experiment in printing that never caught on, a brilliant prototype that died with its creator? The Phaistos disk offers no answers, only a silent, stubborn challenge. It is a haunting reminder that some doors to the past remain firmly locked, and that the greatest inventions are meaningless if the knowledge of how to use them vanishes without a trace. While the Phaistos disk presents a mystery of information lost, our next wonder is a message written not in symbols, but in metal, a statement of triumph that has endured, utterly defiant of time, for over 16 centuries. In the heart of a bustling modern city, surrounded by the sounds and smells of contemporary life, stands a silent sentinel from an age of emperors and empires. This is the Iron Pillar of Delhi, a 23-foot-tall, 6-ton column of pure wrought iron that was forged in the 4th century, and it possesses a property that seems to defy the laws of nature. It does not rust. In a region known for its oppressive monsoon humidity, where modern steel structures require constant painting and maintenance to fight a relentless battle against corrosion, this ancient pillar has stood exposed to the elements for 1,600 years without showing any significant signs of decay. It is not sheltered in a climate-controlled museum. It stands in the open air, a testament to a metallurgical genius that we are still working to fully comprehend. The pillar's origin is as grand as its appearance. An inscription in Sanskrit, carved into its surface, reveals it was erected as a standard to honor a mighty king, most likely Chandragupta II of the Gupta Empire, a period often called India's Golden Age. It was originally located elsewhere, possibly at a site called Udayagiri, and topped with an image of the divine bird Garuda, before being moved to its current location centuries later. But the true marvel is not its history, it is the material from which it is made. The pillar is constructed from astonishingly pure wrought iron. Modern analyses show it contains about 98% iron, an exceptionally high purity level that indicates a masterful control over the ancient smelting process. This was achieved through a technique called the bloomery process, where iron ore was heated with charcoal in a small furnace. The craftsmen, known as lohars, would repeatedly heat and hammer the resulting metallic bloom, skillfully squeezing out the slag impurities with each strike. The fact that they could produce such a massive, homogeneous object of such purity through this labor-intensive method is a staggering achievement in itself. However, purity alone cannot explain the pillar's legendary resistance to rust. The secret lies in a thin, protective film that is formed on its surface, an invisible shield only a few hundredths of a millimeter thick. This layer is not a modern polymer or a special coating applied by its creators. It is a self-forming barrier called mesawite, a complex compound of iron, oxygen, and hydrogen. For a long time, it was thought that the pillar's high phosphorus content was the key. The iron used by the Gupta metalworkers had a phosphorus level about 10 times higher than that of modern iron, a result of the specific ores and the charcoal they used. The theory was that this phosphorus, along with the absence of damaging elements like sulfur and manganese, helped catalyze the formation of this protective passive layer. The process is slow and natural. Over decades of exposure to the environment, the initial, thin layer of rust interacted with the phosphorus-rich metal beneath it, transforming into this stable, non-porous coating that actually prevents oxygen and moisture from penetrating deeper and causing further corrosion. It's a perfect example of a passive layer, similar in function to the protective oxide that forms on stainless steel, but achieved through entirely different, and in some ways more forgiving, ancient means. Yet, the story is even more nuanced than that. Recent research suggests that the specific climatic conditions of Delhi play a crucial role. The pillar's longevity may be due to the relative low humidity for most of the year, punctuated by a distinct wet season. This cycle, rather than constant dampness, might be the ideal recipe for the formation and maintenance of the mesawite layer. This presents a humbling challenge for modern engineers. We can create stainless steel, of course, but that requires adding expensive alloys like chromium. The dream of creating a bulk, low-carbon iron that is as naturally resistant to corrosion as the Delhi pillar, using a simple and potentially more sustainable process, has proven elusive. Attempts to replicate the conditions have had mixed results, indicating that the ancient Lohars benefited from a fortunate, and perhaps not fully understood, combination of material composition and environmental exposure. They achieved through empirical skill, and perhaps a bit of serendipity, what our advanced science still grapples with. The Iron Pillar of Delhi, therefore, is more than just an old artifact. It is a living lesson in materials science. It stands not merely as a monument to a forgotten king, but as a timeless tribute to the anonymous craftsmen whose intuitive understanding of their craft created something that modern technology still regards with a sense of awe and mystery. Leaving behind the silent, stoic endurance of the Iron Pillar, we now travel to a world of noise, motion, and pure, unadulterated wonder. Imagine the great library of Alexandria at its zenith, a repository of all human knowledge, where the finest minds of the ancient world gathered to push the boundaries of science and mathematics. Among these geniuses was a man named Hero, an engineer and inventor whose creations seemed to border on magic, and of all his wondrous devices, one stands out as a breathtaking glimpse of a future that never was, a simple, elegant sphere that whirled and hissed with the power of steam. This was the eolipile, and its existence proves that the fundamental principle of the Industrial Revolution was not only understood, but demonstrated, a full 17 centuries before it would change the world. Hero's device, described in his work, Pneumatica, was deceptively simple in its construction. Picture a hollow metal sphere, suspended between two pivots so it could rotate freely. Two L-shaped tubes extended from these pivots into the sphere, acting as nozzles. The sphere was partially filled with water, and beneath it, a fire was lit, heating a sealed cauldron. As the water boiled, steam rushed up through the pivots and into the sphere, where it was forced out at high velocity through the two opposing nozzles. According to Newton's third law, every action has an equal and opposite reaction. The force of the steam jets shooting outwards caused the sphere itself to spin in the opposite direction. The result was a whirling, steaming metal ball, a primitive but perfectly functional steam turbine. It wasn't just a toy. It was a working model of a heat engine, converting thermal energy into mechanical motion. The basic physics that would one day power locomotives and factories was right there, spinning in a temple courtyard in the 1st century. So, the inevitable, haunting question arises. Why did this remarkable invention remain a fascinating curiosity, a mere parlor trick for the intellectual elite, rather than the spark that ignited an ancient industrial revolution? The answer is not a simple failure of imagination, but a complex interplay of economics, society, and practicality. First and foremost, the ancient world lacked a pressing economic incentive to replace its existing power sources. The Roman Empire, in which Hero lived, was built on the backs of abundant and cheap labor in the form of slavery and widespread indentured servitude. Why would a wealthy landowner invest vast sums in developing a complex, untested steam engine to power a mill or a mine when human muscle power was so readily available and inexpensive? The cost of developing the technology from a prototype into a practical, large-scale machine would have been astronomical, with no clear economic return. The eolipile was a brilliant demonstration of a principle. But translating that principle into a useful machine required metallurgy advanced enough to build high-pressure boilers that wouldn't explode, and precision engineering to create pistons and gears that could handle continuous, heavy loads technologies that simply didn't exist yet. Furthermore, the ancient mindset towards technology was fundamentally different from our own. For thinkers like Hero, machines were often seen as thaumaata, wonders or marvels designed to illustrate philosophical principles, to inspire awe in religious contexts, or to simply demonstrate the cleverness of the inventor. They were creations for temples and royal gardens, not for factories and farms. The concept of technological progress as an endless, linear march towards greater efficiency and productivity is a largely modern idea. The ancient world valued stability, tradition, and philosophical contemplation. A device like the eolipile was celebrated for its ingenuity and its ability to mimic the powers of nature, not for its potential to disrupt the social and economic order. There was no widespread drive to mechanize production because the very idea of mass production for a consumer society was millennia away. The engine remained a fascinating dead end, a seed of genius that fell on stony ground, lacking the social and economic soil needed to grow. It is a profound testament to the fact that a great invention is not enough. It must arrive in a world that is ready to receive it. Hero of Alexandria possessed the spark, but the ancient world lacked the tinder to start the fire. Now, let's shift our focus from the grand scale of temples and engines to something intimately personal. A discovery that speaks to one of humanity's most universal fears and a very modern solution. The idea of a dentist's drill is enough to make many of us flinch today, with all our numbing agents and high-speed tools. It's a sensation we associate squarely with the modern world. But what if I told you that the practice of drilling teeth is, in fact, one of the oldest specialized medical procedures ever discovered? Evidence unearthed at the Neolithic site of Mehrgarh, in present-day Pakistan, has completely rewritten the history of medicine. Here, in a settlement dating back an astonishing 9,000 years, to around 7,500 BCE, archaeologists found human remains with a startling feature. Several teeth, from at least 9 different individuals, showed clear, precise holes drilled into them. This wasn't damage from chewing hard food or accidental trauma. These were carefully crafted, conical cavities bored directly into the chewing surface of the molars. A deliberate act of surgical intervention that predates the invention of writing by over 4,000 years. The sophistication of this procedure is what truly staggers the imagination. These Neolithic dentists weren't working with polished steel. Their drill bits were made of flint, a hard, sharp stone that could be chipped into a fine point. Think about the skill and control required. Using a small, bow-like tool to spin the flint tip, a healer would have had to apply just the right amount of pressure to slowly grind through the hard enamel and into the softer dentin beneath, all without shattering the tooth or causing irreparable damage to the pulp and nerve inside. It was a painstaking, delicate operation that undoubtedly required a steady hand and a deep understanding of human anatomy. The motivation seems clear: to remove decayed tissue, to relieve the pressure and agony of an abscess, or perhaps even to drain an infection. This was not mere superstition. It was a pragmatic, mechanical solution to a common and debilitating problem. But the story becomes even more remarkable. Analysis of some of these ancient teeth revealed traces of a dark substance lining the drilled cavities. This material was identified as bitumen, a natural tar-like substance. The presence of this material suggests something groundbreaking. It appears that after the decay was scraped out, these early practitioners filled the hole, possibly to seal it from food particles and to reduce sensitivity. This use of bitumen represents the world's earliest known dental filling, a concept so advanced that it wouldn't become standard practice again for millennia. This transforms the procedure from a simple act of drilling into a comprehensive treatment: diagnose, excavate, and restore. This discovery at Mehrgarh forces a dramatic reassessment of prehistoric life. We often picture our Neolithic ancestors as struggling for mere survival, their lives consumed by the hunt for food and shelter, with little room for specialized knowledge or advanced healthcare. The evidence of these drilled teeth shatters that image. It reveals a society stable and sophisticated enough to support specialized healers individuals who had accumulated and passed down specific knowledge about a complex surgical technique. This wasn't a one-off experiment. The fact that it was performed on multiple individuals over a significant period indicates an established, recognized medical tradition. It stands as a powerful, intimate testament to humanity's enduring desire to alleviate suffering, a spark of medical genius that flickered brightly in the dawn of civilization, only to be lost and then laboriously reinvented thousands of years later. We've seen ancient minds master mechanics, chemistry, and even medicine, but now we encounter an object that seems to defy logic itself, a piece of ancient art that plays with light in a way that appears almost supernatural. This is the Lycurgus Cup, a magnificent Roman artifact from the 4th century, and it holds a secret that would not be scientifically understood for another 1600 years. At first glance, under reflected light, the cup appears a murky, opaque jade green, but hold it up to a light source, let the light shine through it, and the entire vessel undergoes a miraculous transformation. It glows a vibrant, translucent ruby red. This is not a trick of the light or a simple pigment. It is a stunning display of ancient nanotechnology, a happy accident of Roman craftsmanship that manipulated matter at a scale invisible to the human eye. The cup itself is a masterpiece of Roman diatritum, or cage cup, glasswork. It's a small decorative beaker, carved from a single thick block of glass. Skilled artisans then meticulously cut away the majority of the material, leaving behind an exquisite figural scene set within a delicate, lacy cage of glass that stands out from the main body. The scene depicts the mythical king Lycurgus of Thrace, entangled in vines as a punishment for denying the god Dionysus, but the true wonder of the cup isn't its intricate carving, it's the material from which it is made. For centuries, the secret of its color-changing property was a complete mystery, a lost art that even the most skilled glassmakers could not replicate. The answer was finally revealed in the 1990s, thanks to the powerful magnification of electron microscopes. When scientists analyzed a tiny fragment of the glass, they discovered that the Roman artisans had, completely unknowingly, created a sophisticated nanoparticle colloid. They had infused the molten glass with a precise, minuscule amount of powdered metals, gold and silver, but this wasn't just a simple mixture. The process of heating and cooling the glass, combined with the repeated grinding and polishing, caused the metal particles to be ground down to an unimaginably small size, between 50 and 100 nanometers in diameter. To put that in perspective, a nanometer is 1/1000th of a meter. These particles are about 1,000 times smaller than the width of a human hair. At this infinitesimal scale, the particles are small enough to interact with light in a unique quantum mechanical way, a phenomenon we now call dichroism. Here's the science behind the magic. The gold and silver nanoparticles suspended in the glass act as tiny antennas for light. When light hits the cup from the outside, in what's called reflected light, the nanoparticles primarily scatter the green and blue wavelengths of the visible spectrum. Our eyes, therefore, perceive the cup as green, but when a light is placed inside the cup and the light travels through the glass, the nanoparticles absorb the blue and green wavelengths and allow the red wavelengths to pass straight through. This is why the cup glows a brilliant, fiery red when backlit. The Romans had, through empirical experimentation and masterful control of their materials, stumbled upon the principles of what we now know as plasmonics, the study of how light interacts with nanoscale metallic structures. Perhaps the most astounding part of this story is that the creation of this effect was almost certainly accidental. The Roman glassmakers weren't following a precise scientific formula. They were likely trying to achieve a simple red color, a common goal using colloidal gold, and through a specific, and perhaps not fully controlled, process of mixing and heating, they achieved this extraordinary dichroic effect. They then recognized its beauty and uniqueness, preserving the technique for this one incredibly special object. There are only a few other fragments of Roman glass that exhibit this same property, suggesting the knowledge was rare and may have died with the artisans who perfected it. The Lycurgus Cup is a breathtaking intersection of art and accidental science. It stands as a silent, shimmering monument to the fact that the ancients were not just skilled craftsmen. They were pioneers who, without even knowing it, ventured into a realm of materials science so advanced that it would take the invention of the electron microscope for us to finally comprehend their genius. Our journey now takes us from the controlled artistry of Roman glass to a dusty rock shop in California, and to a discovery so bizarre it seems ripped from the pages of a science fiction novel. In 1961, 3 men were prospecting for geodes near the town of Valencia in the Coso Mountains. Geodes, for those unfamiliar, are plain-looking rocks that conceal a hollow interior lined with beautiful crystals. Hoping to find valuable specimens, the men used a diamond-edged saw to cut open what appeared to be a promising nodule. Inside, they did not find the expected sparkling crystals of quartz or amethyst. Instead, they found something utterly impossible, a mechanical object. At the center of the rock was a circular section of hard, white material, and through its center ran a 2-millimeter thick shaft of shiny metal. The object was unmistakably familiar. It looked exactly like a modern spark plug. This was no ordinary rock. The outer layer was a hard shell of hardened clay, pebbles, and fossil shells, which geologists would later identify as a concretion, a type of rock that forms around a nucleus when mineral-rich water deposits layers over time. The discoverers, Wallace Lane, Virginia Maxey, and Mike Mikesell, were astounded. They took their find to a geologist, who allegedly examined the encasing material and declared that the nodule had to be at least 500,000 years old. The story, publicized in a gem and mineral magazine, sent shockwaves through fringe science circles. Here was the ultimate out-of-place artifact, or OOP art, a 20th-century industrial object seemingly sealed inside a stone that predated modern humans by hundreds of thousands of years. The implications were staggering. Could it be evidence of a highly advanced prehistoric civilization, like Atlantis or Mu? Was it a piece of machinery left behind by ancient astronauts? Or could it be proof of time travelers, accidentally dropping a spark plug 500,000 years in the past? Of course, the scientific community was immediately skeptical, and for a very good reason. Context is everything in archaeology. An object's true age isn't determined by the object itself, but by the undisturbed geological layer in which it is found. The Coso artifact had not been excavated by archaeologists from a documented, deep stratigraphic layer. It was found lying on the ground by collectors. This single fact undermines its entire mystery. Without a clear, verifiable context, there is no way to prove the geode formed around the spark plug. The most logical explanation is that the spark plug was already there, and the concretion formed against it much more recently. Concretions can form surprisingly quickly, in a matter of decades, not millennia, under the right conditions. The key to solving the mystery lay in identifying the object itself. The original artifact mysteriously disappeared from public view after the 1960s, making modern analysis impossible. However, investigators like Pierre Stromberg and Paul Heinrich eventually cracked the case by examining clear photographs. They identified the object not as an alien relic, but as a champion spark plug from the early 1920s, a model commonly used in Ford Model T and Model A engines. The ceramic interior was the spark plug's porcelain insulator, and the metal shaft was the central electrode. This specific type of spark plug had a threaded metal shell that was often corroded away, which explained why the discoverers saw a smooth, circular form. The geode itself was not a true geode at all, but an iron concretion, a type of rock that forms very quickly around iron objects in moist, oxidizing environments. The area where it was found was littered with old mining equipment and discarded machinery from the late 19th and early 20th centuries. The most plausible scenario is that a spark plug from an old truck or mining vehicle was discarded on the ground sometime in the 1920s. Over the next 40 years, mineral-rich water percolated around it, forming a hard, rock-like concretion that encased the object, making it appear as if it had been there for eons. The story of the Coso artifact is a classic cautionary tale. It highlights the immense importance of rigorous scientific method and the dangers of jumping to extraordinary conclusions. It teaches us that our desire to find evidence of lost advanced civilizations or visitors from other worlds can sometimes lead us to see mysteries where none exist. The real lesson of the Coso artifact isn't about ancient technology, It's about critical thinking. It reminds us that the true work of understanding the past is slow, meticulous, and often less glamorous than a headline-grabbing anomaly. It forces us to ask not just, what is this object, but how did it get here, and what is the simplest explanation that fits all the facts? In the end, the spark plug in the stone is a powerful testament not to ancient astronauts, but to the fascinating and surprisingly rapid processes of geology, and to the human tendency to find wonder in the ordinary when it appears out of place. While the Lycurgus Cup showcases an accidental marvel of Roman nanotechnology, our next invention represents a deliberate and systematic attempt to understand the violent forces of nature itself. In the year 132, during the Han Dynasty of China, a brilliant astronomer, mathematician, and engineer named Zhang Heng presented the court of Emperor Shun with a device that must have seemed like something from a myth. It was a large, ornate bronze vessel, perhaps 6 feet in diameter, adorned with 8 dragons snaking down its sides. Each dragon held a bronze ball firmly in its jaws, and directly below each dragon, with its mouth wide open, sat a bronze frog. This was not a ceremonial object or a piece of art, though it was certainly beautiful. This was the world's first seismoscope, an instrument designed to detect earthquakes from incredible distances, and its effectiveness was proven in a legendary account that has echoed through the centuries. The principle behind the device was as elegant as its appearance. Zhang Heng understood that seismic waves, the vibrations traveling through the earth from a distant earthquake, could be detected. His invention was essentially a sophisticated motion detector. Historical records describe a startling incident where one of the dragons suddenly released its ball, which dropped with a loud clang into the mouth of the waiting frog. The court, located in the capital city of Luoyang, felt no tremors whatsoever and was initially skeptical. Yet, several days later, a messenger arrived from a region hundreds of miles to the west, reporting that a major earthquake had indeed struck there on the very day the dragon had spat its ball. The seismoscope had not only detected the quake, but had accurately indicated its direction. The great mystery that has captivated historians and engineers for centuries is this: what hidden mechanism was inside that bronze jar? How could it distinguish the subtle, specific vibrations from a single direction while ignoring all other local shaking? Zhang Heng's original writings on the internal workings have been lost, leaving us with only the external description. The most widely accepted theory, and the one that seems most plausible, involves an inverted pendulum. Imagine a heavy mass suspended by a delicate pivot or a flexible rod from the top of the vessel, hanging down in the center. This pendulum would act as the sensitive heart of the device. The jar itself had 8 channels leading to the 8 dragons, likely containing some kind of lever mechanism. When seismic waves arrived from a specific direction, say, the west, they would cause the entire jar to jolt. But the suspended pendulum, due to its inertia, would tend to stay still relative to the moving Earth. This relative motion would cause the top of the pendulum to swing in the opposite direction of the shockwave, in this case, toward the east. This swing would then trigger a lever mechanism inside the east-facing channel, which would release a catch, allowing the dragon on the western side of the vessel to drop its ball. It's a concept of brilliant simplicity, using basic physics to solve a complex problem. The direction of the pendulum's counter-swing reliably indicated the epicenter's bearing. Other theories have been proposed, including a system of balanced metal balls resting on slight inclines that would be dislodged by the vibrations, but the inverted pendulum theory remains the strongest. It accounts for the device's reported sensitivity and its ability to pinpoint direction. The true genius of Zhang Heng's seismoscope lies in its conceptual leap. He moved beyond superstitious explanations for earthquakes' angry gods or mythical creatures, and proposed a physical, measurable cause. He created an instrument that extended human perception, allowing the court to feel a disaster far beyond the horizon. It was a tool for governance as much as for science, enabling the swift dispatch of aid to afflicted regions. This single device stands as a powerful symbol of ancient China's advanced scientific culture, a civilization that sought not just to live within nature, but to understand its rhythms and warn against its dangers. Our journey now takes us from the settled ingenuity of ancient China to the windswept, wave-tossed decks of Viking longships, where survival depended not on grand monuments, but on a more immediate kind of genius, the ability to find one's way across a trackless, unforgiving ocean. The Vikings' legendary voyages across the North Atlantic, reaching as far as North America 5 centuries before Columbus, are a feat that has long baffled historians. They crossed thousands of miles of open water, far beyond the sight of any land, navigating under skies that were notoriously overcast and foggy for much of the year. The magnetic compass was still unknown in Europe at this time, so how did they do it? The sagas offer a tantalizing clue, mentioning a mysterious object called a solarstein, a sunstone. This wasn't a mythical gemstone of fantasy. It was a practical navigational tool, a crystal that could, according to the tales, reveal the position of the sun even when it was completely hidden behind clouds or had just dipped below the horizon. For centuries, this was dismissed as mere poetic license, but modern science has revealed that the sunstone was not only plausible, but it was almost certainly a key piece of Viking technology, harnessing a fascinating optical property of a common mineral. The likely candidate for this legendary stone is a crystal known as Iceland spar, a perfectly transparent form of calcite that is found, as the name suggests, in Iceland. This crystal possesses a unique property called double refraction, or birefringence. If you were to place a piece of Iceland spar over a single dot on a piece of paper, you would see not one dot, but two. This is because the crystal splits a single beam of light into 2 separate beams, each vibrating in a different direction and traveling at slightly different speeds through the crystal. But the Vikings weren't using it to look at dots on paper, they were using it to analyze the sky itself. Even on a completely overcast day, sunlight is polarized. As sunlight passes through Earth's atmosphere, it scatters, and the light that reaches us from a 90-degree angle away from the sun itself becomes polarized, meaning its light waves vibrate predominantly in one direction. Our human eyes cannot detect this polarization pattern, but a crystal like Iceland spar can. The proposed method for using the sunstone is both simple and brilliant. A Viking navigator would hold the clear calcite crystal up to the sky, peering through it. They would then slowly rotate the stone. When looking through the crystal, the sky would appear to have 2 different brightnesses because of the double refraction. The navigator's task was to rotate the crystal until both images, or both beams of light passing through it, appeared exactly equally bright. At that specific angle of rotation, the crystal's orientation would point directly toward the hidden sun. It was a way of using the crystal as a filter to decode the invisible signature of sunlight in the atmosphere. Some experimental archaeologists have even suggested that the most skilled navigators could have used the stone at twilight, just after the sun had set, to locate its position below the horizon with enough accuracy to establish a true east-west line. This would have been an invaluable tool for dead reckoning on long voyages, allowing them to correct for the drift caused by ocean currents and winds. What makes this theory so compelling is that it has been tested with remarkable success. In 2011, a team of researchers led by Guy Rapars conducted an experiment using a genuine Iceland spar crystal. They demonstrated that even with the sun as much as 7 degrees below the horizon, a point at which the sky appears uniformly dark to our eyes, the crystal could still determine the sun's position with an accuracy of within 1 degree. This level of precision is more than enough for practical navigation. Furthermore, an intriguing archaeological discovery lends physical weight to the saga stories. A wreck of an English warship from the 1500s, sunk off the coast of the island of Alderney, was found to contain a small, rectangular block of Iceland spar. While this is a later period, it strongly suggests that the navigational use of such crystals persisted in maritime traditions long after the Viking Age, a secret technique passed down among sailors. The Viking Sunstone, therefore, stands as a perfect example of pragmatic ancient innovation. It required no complex machinery, no advanced metallurgy. It was a product of deep, empirical observation of the natural world. The Vikings recognized a unique property in a mineral they had access to, and they applied that property to solve one of the most critical challenges of their age. They didn't need to understand the wave theory of light or the physics of polarization. They simply needed to know that if you rotated the stone until the light looked a certain way, it would keep your ship on course. It was a tool born of necessity, a crystalline key that unlocked the secrets of the sky and allowed a seafaring people to conquer the vast, empty reaches of the North Atlantic with a confidence that would not be matched for centuries. To truly grasp the significance of the Antikythera Mechanism, we need to appreciate the intellectual ecosystem that produced it. This wasn't a fluke or a one-off marvel. It was the product of a Hellenistic golden age of science, a period when thinkers in Alexandria and elsewhere were pushing the boundaries of knowledge in ways that would not be seen again until the Renaissance. The device is a physical manifestation of a profound philosophical shift, the idea that the universe operates according to mathematical laws, and that those laws can be modeled mechanically. The level of astronomical understanding encoded in its gears is staggering. It didn't just track the sun and moon in simple circles. It incorporated sophisticated lunar theory developed by astronomers like Hipparchus, accounting for the moon's variable speed in its elliptical orbit through a clever pin and slot mechanism that created a subtle speeding up and slowing down. This required an advanced grasp of geometry and cyclic patterns that was centuries ahead of its time. The engineering itself is a masterpiece of miniaturization and optimization. Creating a gear train with over 30 interlocking bronze wheels, some with teeth cut with such precision that they meshed perfectly, required an understanding of prime numbers and ratios to avoid interference. The presence of a differential gear, a component that allows for the calculation of relative motion, is perhaps the most jaw-dropping feature. This is the same principle that allows the wheels of a modern car to turn at different speeds when cornering. In the mechanism, it was used to subtract the effect of the lunar cycle from the solar cycle to display a calendar of upcoming Olympic Games. This isn't just simple clockwork, it's a programmable analog computer, where the arrangement of the gears themselves constitutes the software. The mind that designed this was thinking in terms of systems, feedback, and interconnected variables. This level of sophistication forces us to wonder, if this one device survived by chance at the bottom of the sea, what else was lost? The writings of ancient engineers like Ctesibius and Philo of Byzantium describe a world filled with technological wonders that sound like science fiction. There were automated puppet theaters powered by water, weights, and compressed air, capable of performing entire mythological plays. Ctesibius is credited with inventing a water organ and sophisticated water clocks that kept accurate time. Heron of Alexandria, whom we've already met, described vending machines that dispensed holy water when a coin was inserted, and automatic doors for temples powered by steam or heated air. It is not a stretch to imagine that the Antikythera Mechanism was not unique, but part of a thriving tradition of complex mechanical devices, perhaps even a school of thought dedicated to what we would now call mechatronics. The tragic reality is that this technological peak was abruptly cut short. The political instability, wars, and eventual decline of the Hellenistic world, followed by the rise of the Roman Empire, which prioritized practical engineering like aqueducts and roads over theoretical science and intricate mechanics, caused this branch of knowledge to wither. The Library of Alexandria, the great repository of this learning, suffered repeated destruction. The intricate art of crafting such precise gear trains was lost, and the philosophical drive to model the cosmos with machines faded away. For over a millennium, the technological ceiling for complex machinery was dramatically lower. The Antikythera Mechanism thus stands as a silent, corroded monument to a road not taken, a vivid demonstration that human progress is not a guaranteed upward climb, but a fragile path that can be lost as easily as a single shipwreck on a stormy day. The terrifying effectiveness of Greek fire on the open water was matched only by the ingenuity of its deployment system. This was not a weapon that could be hurled in pots or fired from a catapult. Its true power was unleashed through a piece of military hardware as advanced as the chemical mixture itself, the pressurized siphon. These were not simple tubes. Mounted on the prows of specialized Byzantine warships called dramens, the siphons were complex bronze contraptions, often crafted to resemble the heads of fearsome lions or other mythical beasts, their gaping mouths serving as the nozzles. The psychological impact of this alone cannot be overstated. Imagine being a sailor on an opposing ship, seeing these monstrous metal heads pointed at you, knowing that at any moment, they could vomit forth an unstoppable stream of liquid hell. The process of firing was a carefully orchestrated maneuver. Historians believe the mixture was stored in large, heated, pressurized tanks below deck. When the enemy was within range, perhaps 50 feet or so, a pump operator would work a large, piston-driven force pump, while another crew member, the siphonarios, would aim the bronze tube using a movable mount. A preliminary charge, likely a flammable substance on a spear tip, was applied to the nozzle to ignite the liquid as it jetted forth. The result was a continuous, roaring blast of fire that could arch over the water and drench an enemy vessel. The tactical advantage was overwhelming. While other navies relied on ramming, boarding, or inaccurate projectile weapons that required closing to point-blank range, the Greek fire siphon allowed the Byzantines to attack from a relative distance, incinerating enemy ships and their crews long before they could mount an effective counter-assault. The flaming jet would cling to sails, rigging, and wooden hulls, and most devastatingly, it would settle on the water's surface, creating a burning moat around the target that prevented escape and could even set other ships ablaze. It was the ancient equivalent of a flamethrower, a weapon of area denial and pure terror that could break a fleet's formation and morale in moments. The secret of Greek fire's composition was so closely guarded that it became a matter of state security. Knowledge was compartmentalized. The chemists who prepared the mixture likely knew only part of the recipe, while the imperial family held the complete formula. This extreme secrecy, while successful in preventing the technology from falling into enemy hands for centuries, ultimately proved to be its Achilles heel. As the Byzantine Empire faced gradual decline, buffeted by internal strife, the Crusades, and relentless external pressure, the fragile chain of knowledge was broken. The exact recipe, the precise proportions, and the engineering subtleties of the pressurized siphons were lost. It wasn't a single catastrophic event that erased Greek fire, but a slow fade, a death by 1,000 cuts to the institutional knowledge that had sustained it. Modern attempts to recreate Greek fire have been numerous, but all have fallen short of the terrifying descriptions left by both Byzantine and Arab chroniclers. Chemists and historians generally agree on a base of crude petroleum or naphtha, but the secret ingredient that allowed it to ignite on contact with water and burn so fiercely remains elusive. Many experiments point to quicklime calcium oxide, which heats up dramatically when wet, as a potential catalyst. Others suggest additions like sulfur, saltpeter, or even pine resin to create a thicker, more adhesive napalm-like substance. Yet, no modern reconstruction has consistently produced a substance that perfectly matches the historical accounts, particularly its reported resistance to being extinguished by water, which only seemed to spread the flames. The loss was absolute. This loss had dire consequences. Greek fire was the cornerstone of Byzantine naval dominance for over 500 years. It was the great equalizer that allowed a shrinking empire to defend its capital against numerically superior foes. Once it was gone, that critical advantage vanished. The Byzantine navy could no longer project the same overwhelming power, and its control over the Mediterranean sea lanes slowly eroded. The disappearance of Greek fire is a stark lesson in the fragility of technology. It demonstrates that an invention, no matter how powerful, is not a permanent possession. It must be nurtured, documented, and passed down through generations, or it can simply slip through the cracks of history, leaving behind only legends of its fearsome power and a lingering question of what might have been. To truly grasp the monumental impact of their concrete, we need only stand inside the Pantheon in Rome. That vast, breathtaking dome, spanning 143 feet, was an architectural dare that defied gravity for centuries. It remains the world's largest unreinforced concrete dome, a record it held for over 1,300 years. The Romans didn't just build a roof, they built a sky. The genius of its construction lies in the gradual alteration of the concrete mixture from the base to the very top. At the heavy, foundational levels, the builders used dense, sturdy aggregates like travertine. But as the dome curved ever upward, they lightened the load by mixing in progressively lighter materials, including pumice and even hollow terracotta pots. This careful engineering, combined with the incredible cohesive strength and durability of their pozzolana-laced concrete, created a structure that has weathered earthquakes, invasions, and 2 millennia of Roman weather without a single major crack. It is a silent sermon on the power of building for eternity. This same material enabled another foundation of Roman civilization, the aqueducts. These were not mere decorative arches, but the arterial system of the empire, carrying fresh water for miles across valleys and plains. The Pont du Gard in southern France is a staggering 3-tiered bridge, standing 160 feet high, that supported a water channel at its peak. What's astonishing is the mortar used to hold the massive, precisely cut stones together. Unlike the concrete used for the Pantheon's cast dome, here the pozzolana-based mortar provided a hydraulic setting, meaning it could cure and gain strength even when completely submerged in the water flowing through the channel above. This resilience against constant moisture is something modern Portland cement struggles with, yet the Romans perfected it. These aqueducts, built to last forever, functioned for centuries, supplying public baths, fountains, and private households, enabling the growth of cities on an unprecedented scale. Creating this miracle material on an empire-wide scale was a logistical undertaking of staggering proportions. The key ingredient, pozzolana ash, was not universally available. The highest-quality deposits were found primarily around the Bay of Naples, near the city of Pozzuoli. This meant that for major construction projects across the Mediterranean world, from the ports of Caesarea in Judea to the cities of North Africa, this specific volcanic ash had to be mined, bagged, and shipped. Imagine the fleets of merchant vessels, their hulls heavy with sacks of this gray, sandy powder, becoming a common sight in ports throughout the empire. The Romans, masters of organization and supply chains, treated pozzolana not as a local curiosity, but as a strategic resource, essential for stamping their architectural identity on every conquered province. They understood that the extra cost and effort of transporting this specific material over vast distances were investments in permanence. This brings us to the most profound contrast between their world and ours, the philosophy of time. Roman engineers and their patrons, often the state itself, operated with a long-term perspective that is almost alien to modern economics. They built with the explicit intention that their creations would serve generations unborn. The Pantheon, the aqueducts, the roads, these were legacy projects, meant to echo the glory of Rome for all time. Our contemporary construction industry, by comparison, is often governed by different priorities: speed, initial cost efficiency, and projected lifespans that rarely exceed 50 to 100 years. We use reinforced concrete, which is incredibly strong but has a critical weakness. The steel rebar inside is vulnerable to corrosion from water and salt, which causes it to expand and crack the concrete from within. This creates a cycle of decay and costly repair that the Romans cleverly avoided with their self-healing, non-metallic formula. The lesson of Roman concrete is not merely a technical one, it is a philosophical challenge. It forces us to question our own values. Are we building a disposable world? The Romans show us that it is possible to create infrastructure that grows stronger with age, that becomes a gift to the future rather than a burden. Today, as civil engineers and scientists urgently study the molecular secrets of ancient Roman harbors, they are not doing so out of mere historical curiosity. They are seeking answers to our own modern crisis of crumbling bridges and decaying roads. In decoding the recipe for this 2,000-year-old material, we are rediscovering a wisdom that prioritizes resilience over rapidity and longevity over immediate profit. The silent, enduring strength of Roman concrete is a testament to a civilization that looked to the horizon of centuries, and in doing so, built a legacy that literally still stands over us today. From the stone and mortar of Roman construction, we now turn to the mastery of metal, where ancient smiths transformed base elements into materials of legendary strength and beauty. Our next two inventions represent twin peaks of metallurgical genius from opposite ends of the ancient world. First, from the forges of India and the swordsmiths of Damascus, came a steel so superior it became the stuff of myth. And second, from the blast furnaces of ancient China, flowed rivers of cast iron on an industrial scale that Europe would not achieve for over 1,000 years. These were not just incremental improvements, they were revolutionary leaps in mankind's ability to shape the very substances of the earth. The story of Damascus steel begins not in Syria, but in the crucibles of India, with a material known as Wootz steel. This was a high-carbon steel produced through an incredibly sophisticated process. Indian metal workers would place iron ore along with specific leaves and other organic materials in a small, sealed clay crucible. This crucible was then heated in a charcoal furnace for an extended period, often several days. Inside this sealed environment, a remarkable transformation took place. The carbon from the organic matter would slowly infuse into the iron, but instead of creating a brittle, high-carbon mass, it formed a solid ingot filled with microscopic structures called carbide bands. This Wootz steel ingot was then traded westward to cities like Damascus, which were famous for their swordsmithing. It was here that the true magic happened. The Syrian smiths possessed a secret art of forging. They would heat the Wootz ingot to a precise, critical temperature, not so hot that it became molten, but just hot enough to make it malleable. Then, with patient, skillful hammering, they would fold and forge the steel, carefully controlling its cooling. This process caused the carbon particles within the steel to align into visible patterns. The famous watery bands or damask that looked like wood grain or flowing water etched onto the blade's surface. But this was far more than just decorative. The resulting blade was a paradox of physical properties. It was famously sharp, capable of holding an edge that could slice a silk scarf floating in the air, yet it was also incredibly tough and flexible, able to bend significantly without snapping. In an era when many swords were either hard but brittle or soft and quick to dull, a Damascus steel sword was the perfect balance. Its reputation was so immense that during the Crusades, European knights returned with tales of Islamic warriors wielding swords that could cleave through their own armor and even cut a knight in half. The secret, however, was not just in the smithing technique. It was an alchemical combination of the specific source iron ore from India, which contained trace impurities like vanadium, and the precise thermal cycles used in its production. This delicate balance of knowledge was tragically lost around the 18th century. The exact reasons are unclear, perhaps the depletion of the unique Indian ore, or the disruption of trade routes, or the dying out of master smiths who passed their knowledge only orally. For centuries, attempts to recreate true Damascus steel have failed. Modern metallurgists, using electron microscopes, have only recently begun to understand the complex nanostructures of carbon nanotubes and carbide nanowires that gave the steel its unique properties, a secret the ancients discovered and perfected through centuries of empirical experimentation, only to see it vanish into the mists of time. While the smiths of Damascus worked on an artisanal scale, creating individual masterpieces of steel, ancient China was achieving something entirely different: the mass production of iron on an almost industrial level. As early as the 5th century BCE, during the Warring States period, Chinese metallurgists developed the blast furnace. This was a game-changing innovation. Unlike the small, inefficient bloomery furnaces used in the West, which produced a spongy mass of iron that required constant hammering to remove impurities, the Chinese blast furnace operated at a much higher temperature. By using powerful bellows to force a continuous blast of air into the furnace, they could fully melt the iron ore. The iron would liquefy and collect at the bottom of the furnace, where it could be tapped out and poured into molds, much like bronze. This process produced cast iron, also known as pig iron. The advantages were monumental. Cast iron could be produced in vast quantities and cast into intricate shapes with relative ease. The Chinese used this capability to revolutionize their society. They mass-produced sturdy iron plowshares and farming tools that increased agricultural yields exponentially. They cast powerful weapons swords, spearheads, and crossbow triggers that equipped massive, standardized armies, but they didn't stop at practical items. They cast enormous artistic works, including life-sized statues and intricate ceremonial vessels. One of the most stunning examples is the 4 great iron lions of Kangju, cast during the 10th century, the largest of which stands over 18 feet tall and weighs more than 40 tons, a testament to a foundry technology of awe-inspiring scale. The Chinese soon realized that while cast iron was hard and excellent for casting, it could also be brittle, so they pioneered another revolutionary process, the conversion of cast iron into steel. By the 2nd century BCE, they had developed a method called fining. They would take a lump of cast iron and heat it in a furnace while subjecting it to a blast of air. The oxygen in the air would burn off the excess carbon in the iron, transforming the brittle cast iron into malleable, low-carbon wrought iron or, with precise control, into steel. This was essentially the Bessemer process, a cornerstone of the modern steel industry, but it was being practiced in China over 2,000 years before it was patented in the West. This continuous cycle, from blast furnace to cast iron to fine steel, created a metallurgical ecosystem that supplied an empire, fueling economic and military power on a scale the world had never seen. It was a systematic, chemical understanding of iron that allowed China to enter its own Iron Age centuries before Europe, building an infrastructure of metal that supported its growth for millennia. The story of these two metalworking traditions is a tale of different paths to greatness. One, a secret art of perfection applied to a single, exquisite object. The other, a science of scale that built an entire civilization out of iron. Moving from the grand scale of metallurgy and construction, we now turn to the most intimate and daring frontier of ancient innovation, the human body itself. The idea of surgery, of deliberately cutting into a living person to heal them, feels like a hallmark of modern medicine, but evidence from across the globe reveals that our ancestors possessed not only the courage to attempt such procedures, but a startling degree of skill and understanding that allowed patients to survive and heal. Two areas in particular stand out, one a seemingly brutal procedure performed with remarkable finesse, and the other a creation of compassionate engineering that restored mobility and dignity. The first is trepanation, the practice of drilling, scraping, or cutting a hole into the human skull. It is one of the oldest known surgical procedures, with evidence stretching back to the Neolithic era, over 10,000 years ago. What is truly astonishing is not just its age, but its geographical spread. Skulls bearing the signs of trepanation have been found in ancient Peru, throughout Europe, in parts of Asia, and in Africa. This was not an isolated practice of a single culture. It was a medical phenomenon that emerged independently across the world. The procedure itself varied. Some practitioners used a sharp piece of flint or obsidian to scrape away the bone in a circular motion. Others used a bow drill, similar to what we saw with Neolithic dentistry, to bore a series of small holes that were then connected. The goal was always the same, to remove a piece of the skull, exposing the protective membrane around the brain, the dura mater. But why would anyone do this? The motivations were likely as varied as the cultures themselves. Ancient texts and anthropological studies suggest it was used to treat a range of conditions. A severe headache, epilepsy, or mental illness might have been interpreted as caused by an evil spirit trapped inside the head. Creating an opening would provide a pathway for the spirit to escape. More practically, it was almost certainly a treatment for head trauma. A warrior who suffered a skull fracture in battle could develop a buildup of blood between the skull and the brain, a condition called a subdural hematoma, which creates intense pressure and is often fatal. Trepanation would relieve that pressure, a life-saving intervention that demonstrates a clear understanding of the connection between physical injury and its systemic effects. The most compelling evidence for its success, however, comes from the bones themselves. Archaeologists can determine if a patient survived the operation by examining the edges of the trepanation hole. A smooth, rounded edge with signs of new bone growth, a process called osteosynthesis, means the individual lived for months or even years after the procedure. Skulls with multiple trepanations, showing several healed holes, are not uncommon, indicating that some individuals underwent this harrowing operation more than once and lived to tell the tale. This survival rate points to knowledge that goes far beyond simple butchery. It implies that these ancient surgeons understood the critical importance of cleanliness, using tools sterilized in fire or alcohol to prevent infection. They likely used natural anesthetics or sedatives derived from plants like coca leaves in South America or opium poppies in the Middle East to manage the unimaginable pain. Trepanation was not an act of savage superstition. It was a calculated, often successful, surgical gamble born of observation and a desperate desire to heal. This same drive to restore function and alleviate suffering is beautifully illustrated by our second example, the world's earliest functional prosthetics. While we might imagine prosthetic limbs as a modern innovation, the ancient Egyptians were crafting remarkably sophisticated replacements over 3,000 years ago. The most famous example is a prosthetic wooden toe, discovered attached to the mummy of a woman named Tabaketenmut, dating from between 900 and 600 BCE. This wasn't a ceremonial object placed in the tomb for the afterlife. This was a device she wore in life. The signs of wear and tear are clear, and its design is a masterpiece of practical bioengineering. Crafted from wood and leather, the toe is not just a crude peg. It was designed with a level of anatomical accuracy and comfort that is deeply impressive. The toe is hinged, allowing it to flex naturally as the wearer walked. It was carefully shaped to match the remaining toes, and it was attached to the foot with a series of leather straps that would have distributed pressure evenly. This attention to ergonomics reveals a profound understanding of the human gait and the importance of balance. For an elderly woman like Tabaketenmut, who likely lost her toe due to complications from diabetes or gangrene, this prosthetic would have been life-changing. It would have allowed her to walk comfortably again, to maintain her balance while carrying water jars or grinding grain, and to participate fully in her community without being defined by her disability. Other examples, like an even older prosthetic toe from a separate burial made of cartonnage, a material akin to papier-mâché, show that the Egyptians were experimenting with different materials to achieve the same goal: functional restoration. These two practices, trepanation and prosthetic design, represent the two faces of ancient advanced medicine. One is an invasive, high-risk intervention that demonstrates a bold understanding of human anatomy and the will to intervene directly in a crisis. The other is a gentle, rehabilitative art that shows a deep empathy for the individual's quality of life and a clever application of materials science to the human form. Together, they shatter the simplistic notion of ancient healthcare as purely magical or herbalistic. They reveal a world where healers were also engineers and surgeons, where the human body was seen as a system that could be repaired, both from the inside out and the outside in. This was a medicine not just of survival, but of compassion and a quiet, determined brilliance that sought to mend what was broken. Now, let's journey from the world of individual healing to the very foundations of civilization itself, to a society that mastered the art of living together on a scale that would not be seen again for thousands of years. While Egypt was building pyramids and Mesopotamia was erecting ziggurats, a remarkably different and in many ways more modern civilization was flourishing in the vast floodplain of the Indus River. The cities of Mohenjo-Daro and Harappa, which emerged around 2500 BCE, present us with a historical anomaly. They lacked the obvious, overwhelming monuments of kings and gods that define other ancient cultures. There are no grand palaces, no colossal statues of rulers, no vast royal tombs filled with treasure. Instead, their genius was channeled into something far more profound: the creation of a functional, healthy, and equitable urban environment. This was a civilization that invested not in the glory of a single individual, but in the well-being of its entire population, achieving a level of civic planning that is nothing short of breathtaking. The first thing that strikes any archaeologist studying Mohenjo-Daro is the layout. This was not a city that grew organically, a tangled maze of alleyways around a central fortress. It was designed. The streets were laid out in a precise grid pattern, with main thoroughfares running north-south and east-west, dividing the city into large blocks. These streets were wide, some over 30 feet across, allowing for the easy flow of people, goods, and air. But the true marvel lies beneath the surface. Almost every single house, from the larger two-story buildings to the more modest single-room dwellings, was connected to an incredibly sophisticated city-wide drainage system. This was not simply a few open gutters. This was a network of covered drains made from carefully fitted, standardized baked bricks. Each house had a bathroom with a sloped floor that directed wastewater into a drain pipe set into the wall, which then emptied into a larger covered channel running under the main streets. These channels were equipped with manholes at regular intervals, allowing for maintenance and cleaning, a concept of public works management that seems remarkably contemporary. The attention to detail in this sanitation system reveals a society with an advanced understanding of public health. The drains were designed with gentle slopes to ensure a constant flow, preventing stagnation. They were covered with brick or stone slabs to contain odors and prevent debris from falling in. Before emptying into the main city drains, the waste from individual houses would often pass through a simple sump or cesspit, which would allow solids to settle, a primitive but effective form of sewage treatment. This concern for cleanliness extended to the water supply. The city featured numerous wells, providing clean, accessible water to neighborhoods. Many larger homes even had their own private wells and bathing platforms. This separation of clean water from wastewater is a fundamental principle of modern sanitation, and the Indus Valley people implemented it on a massive scale over 4,000 years ago. The result was a city capable of supporting a population estimated at 40,000 people, with a remarkably low risk of waterborne diseases like cholera or dysentery, plagues that would regularly devastate crowded cities throughout history until the 19th century. At the heart of Mohenjo-Daro stands one of its most iconic structures, a building that speaks volumes about the culture's priorities, the Great Bath. This is not a vast swimming pool for recreation. It is a carefully constructed, watertight tank, built with finely fitted bricks and sealed with a thick layer of bitumen to prevent leaks. It measures 39 by 23 feet and is 8 feet deep, with steps leading down into it on two ends. Surrounding it are small rooms and a sophisticated water management system, with a large well to fill it and an outlet drain to empty it for cleaning. The purpose of the Great Bath is widely believed to have been ritualistic, a place for communal purification ceremonies, but its very existence underscores the cultural importance placed on cleanliness and water management. It was a public investment in a shared civic and spiritual life, a monument not to a king's power, but to the community's well-being. This level of organization hints at something else extraordinary, a society with a strong, centralized authority, but one that expressed its power differently. The standardization seen throughout the Indus Valley is staggering. The bricks used in Mohenjo-Daro, Harappa, and other cities were manufactured to a uniform ratio. Whether you were in a large city or a small town, the bricks were the same size, suggesting a central authority that controlled production and enforced standards across a vast territory. This standardization made construction faster, more efficient, and more predictable. It speaks of a highly organized administrative system, one capable of coordinating large-scale projects and maintaining a consistent material culture over hundreds of miles. Yet, despite this evidence of planning, there is a conspicuous absence of evidence for a ruling class living in overt luxury. There are no royal palaces significantly larger or more ornate than other buildings. This has led to much speculation that the Indus Valley civilization was perhaps governed by a council of elders or a class of priest-planners, rather than an all-powering monarch, a form of social organization that seems almost utopian in the ancient world. The mystery of the Indus Valley civilization only deepens when we consider its eventual decline around 1900 BC. The reasons are still debated: climate change, the shifting course of the Indus River, or perhaps invasions. But what is truly haunting is the complete loss of their urban planning knowledge. When these great cities were abandoned, their secrets were buried with them. The concept of city-wide, covered sewer systems and grid-patterned streets would vanish from the Indian subcontinent for millennia. Later great cities would be plagued by the very sanitation problems that Mohenjo-Daro had so elegantly solved. The achievements of the Indus Valley stand as a powerful, silent testament to a different path that civilization could have taken, one that prioritized public health, civic order, and communal investment over monumental grandeur. It is a poignant reminder that the height of advancement is not always measured by the tallest tower, but sometimes by the depth and intelligence of the foundations upon which daily life is built. Yet for all the intricate genius of the Antikythera Mechanism and the terrifying power of Greek fire, some of the most transformative ancient inventions were not singular marvels, but robust, practical technologies that steadily changed the daily lives of millions. Among these, few were as quietly revolutionary as the water mill, a device that represents one of humanity's first successful attempts to harness a natural, relentless force, the flow of water, to perform consistent, heavy labor. While heroes Eolipile demonstrated the potential of steam but remained a curiosity, the water mill was a technology that was actually adopted, improved, and spread, laying a crucial piece of the foundation upon which the modern world would eventually be built. The earliest known description of a water mill comes not from the Romans, but from their intellectual predecessors, the Greeks. In the 1st century BCE, the brilliant engineer Philo of Byzantium described a device he called the hydraulites, or water-driven mill. Around the same time, the Roman architect Vitruvius provided a detailed, technical account of its design. The basic principle was straightforward but brilliant. Vitruvius described an undershot water wheel, a large vertical wheel with paddles around its rim. This wheel was mounted over a flowing stream so that the current would push against the bottom paddles, causing the entire wheel to rotate. The key innovation was the connection of this wheel to a grinding stone. Through a simple series of gears, the horizontal rotation of the water wheel was translated into the fast, vertical rotation of a millstone that would grind grain into flour. This was a direct substitution of natural power for human or animal muscle, and it was vastly more efficient. The Romans, ever the practical engineers, saw the immense potential in this Greek invention and ran with it. They didn't just build a few experimental mills, they industrialized the technology. Across the empire, wherever a reliable source of flowing water could be found, Roman engineers constructed mills on a scale that is still impressive today. One of the most spectacular examples was the complex at Barbegal, near Arles in southern France. This was not a single mill, it was an ancient industrial factory. Built in the early 2nd century, the Barbegal mill complex consisted of 2 parallel rows of 8 water wheels each, cascading down a steep hillside. Water from an aqueduct was channeled to the top wheel, which, after doing its work, would discharge its water to power the wheel below it, and so on down the entire slope. This single installation could have produced enough flour to feed the entire population of nearby Arles, estimated at over 10,000 people. It was a breathtaking feat of hydraulic engineering and mass production, a true testament to the Roman capacity for scaling up technology to meet the needs of an urban civilization. But the Roman application of water power didn't stop at grinding grain. There is compelling archaeological evidence that they adapted the water mill for other heavy industrial tasks. The ruins of a Roman settlement at Hierapolis in modern-day Turkey have revealed what appears to be the world's first known water-powered stone sawmill. Here, a water wheel was used to drive a mechanism that moved a frame holding multiple saw blades back and forth, allowing for the efficient cutting of large blocks of marble or stone. This application is profoundly significant. It moves the water mill from the realm of food production, a basic necessity, into the realm of manufacturing and construction. It demonstrates a conceptual leap, understanding that the rotational force of a water wheel could be adapted to create reciprocal, back-and-forth motion for a completely different purpose. This is the essence of mechanization using a single power source to operate a variety of machines. This leads us to a pivotal historical question. With such advanced and widespread use of water power, why didn't the Romans kickstart their own industrial revolution? They had the technological prototype, the engineering skill, and the economic need. The answer lies in a combination of social and economic factors that created a powerful inertia against full-scale mechanization. The Roman economy, particularly in Italy, was fundamentally built on slave labor. Human muscle power was, for the wealthy classes who controlled capital, a cheap and readily available resource. Investing in the construction and maintenance of a complex water mill required significant upfront cost, while purchasing slaves was a one-time expense with a long-term return. There was no burning economic incentive to replace this labor system. Furthermore, the Roman worldview prized stability and tradition. Technology was valued for its ability to solve immediate, practical problems, like feeding a city or cutting stone for a monument, not for its potential to radically transform society and disrupt the existing social order. The water mill was a brilliant tool within the Roman system, but it was not seen as a catalyst for a new system. The true legacy of the Roman water mill was that it preserved and transmitted a crucial idea. When the Western Roman Empire fragmented, the knowledge of this technology did not vanish. It was kept alive in monasteries across Europe, where monks used water mills to grind grain and saw wood, ensuring the technology's survival through the so-called Dark Ages. This continuity is what made the water mill so foundational. It provided a tangible, working model of non-animal power that medieval engineers could later build upon. When the economic and social conditions in Europe finally began to change in the later Middle Ages, with growing populations and rising wages making human labor more expensive, the stage was set. The water mill was already there, waiting in thousands of streams and rivers. It was adapted to power fulling mills for processing cloth, to operate trip hammers for forging iron, and to drive bellows for blast furnaces. This cascade of innovation, which paved the way for the Industrial Revolution, had its direct origins in the practical, widespread, and yet ultimately underutilized water mills of the Roman world. They had created the engine of future change, but lacked the social and economic fuel to start it themselves. From the roaring power of Roman water mills, we now turn to a device of equal genius but far quieter elegance, an invention that moves not with the force of impact, but with the gentle, relentless power of a spiral. Picture a sun-baked field in ancient Egypt, where the life-giving waters of the Nile lie frustratingly low in a canal, while the crops on the higher ground thirst and wilt. How do you lift this heavy, sluggish liquid up to where it is desperately needed, without back-breaking labor? The solution, attributed to one of the greatest minds of antiquity, Archimedes of Syracuse, was a masterpiece of simplicity and profound physical insight: the screw pump. This was not a complex machine of gears and levers, but a beautifully straightforward application of fundamental principles, a device so effective that its basic design remains virtually unchanged after more than 2,000 years. The classic Archimedes screw is a wonder to behold in action. Imagine a long, hollow tube, often made of wood or metal, wrapped around a central cylindrical shaft. Alternatively, it can be a single, continuous helical surface, like a very tight spiral, mounted inside a closely fitting tube. This entire assembly is then positioned at an angle, with the bottom end submerged in the water source and the top end discharging into the higher destination. The true magic begins when the screw is rotated, typically by a hand crank, an animal walking in a circle, or in modern times, an electric motor. As the bottom of the screw turns through the water, individual pockets of water are trapped between the spiral blades. With each rotation, these pockets are carried up the incline of the spiral. The water never flows backwards because the rotating motion and the constant contact with the blades and the tube's wall keep it contained within its individual chamber. It's a continuous process. As one pocket of water reaches the top and spills out, another is being scooped up at the bottom, creating a smooth, non-pulsating flow. The brilliance of this design lies in its exploitation of a few key physical phenomena. First, it uses the principle of the inclined plane, one of the 6 classic simple machines. By wrapping this plane into a spiral, Archimedes effectively created a very long, continuous ramp for the water to climb, but contained within a compact, rotating cylinder. This makes the work of lifting the water far more efficient than trying to haul it up vertically in buckets. Second, it leverages the cohesive and adhesive properties of water, its tendency to stick to itself and to the surfaces it touches. This surface tension helps form the stable pockets that are essential for the screw's operation. The device is remarkably forgiving and low maintenance. It doesn't require perfectly clean water. It can handle water with silt and small debris, which would clog or damage more complex pump mechanisms. It's also energy efficient, as it doesn't need to build up high pressure. It simply coaxes the water upward, one gentle turn at a time. While the invention is famously linked to Archimedes, historical accounts suggest he may have encountered the concept during his travels in Egypt, and then refined or popularized it. Regardless of its true origin, its impact was immediate and lasting. The Romans, always quick to adopt effective technology, used Archimedes screws extensively for irrigation, for draining water from holds of ships, and most notably, for deutering mines. They would install multiple screws in series, each one lifting water to a higher reservoir to drain deep mining pits, a crucial application that allowed them to access mineral wealth that would otherwise have been flooded. This practical utility ensured the screw's survival through the fall of empires. Its legacy is perhaps most visible today in the low-lying countries of Northern Europe. In the Netherlands, a nation famously wrested from the sea, the Archimedes screw has been a cornerstone of water management for centuries. Giant windmill-powered screws were used to pump water out of polders, reclaimed tracts of land, and into higher canals, which would then carry the water out to sea. Even now, in an age of powerful electric pumps, modern versions of the Archimedes screw are experiencing a renaissance. They are being installed in wastewater treatment plants and hydroelectric projects because of their unique advantages. Unlike high-speed centrifugal pumps, which can shred fish and other aquatic life, an Archimedes screw rotates slowly, allowing fish to pass through it unharmed, making it an environmentally friendly choice for moving water in ecologically sensitive areas. Some modern designs are even being used in reverse. Instead of using energy to move water, flowing water is channeled through a large screw, causing it to rotate and generate electricity, a simple and effective form of microhydropower. The enduring power of the Archimedes screw is a testament to a different kind of ancient genius. It wasn't about overwhelming force or intricate complexity. It was about harmonious efficiency. It represents a deep understanding of how to work with the properties of a material, in this case, water, rather than fighting against it. It is a machine that has quietly, reliably, and sustainably served humanity for over 2 millennia, a timeless spiral of innovation that continues to turn, lifting life and powering progress with the same elegant motion that Archimedes himself would have recognized. But the ingenuity of ancient China was not limited to grand civic projects or the mass production of iron. It also expressed itself with deadly precision on the battlefield, where a single mechanical invention became the cornerstone of an empire's unstoppable military machine. We've seen how standardized bricks built the cities of the Indus Valley. Now, we encounter a different kind of standardization, one forged in bronze and designed for conquest. This is the trigger mechanism of the Qin Dynasty crossbow, a deceptively small object that embodies a revolutionary leap in weapons technology, manufacturing, and military doctrine, a leap that would help unify China for the first time. Imagine the scene facing a soldier in the army of the first emperor, Qin Shi Huang, in the 3rd century BCE. He is equipped with a weapon far superior to anything his opponents possess. While enemy armies rely on individual skill with spears and swords, or slow, complex chariots, the Qin soldier raises his crossbow. It's a heavy, stocky weapon, but its power lies not in his muscle alone, but in the intricate bronze box mounted in its stock. This is the trigger mechanism, and it is a masterpiece of engineering. Crafted from several interlocking bronze pieces, it functions with the smooth, reliable precision of a modern firearm. To fire, the soldier simply pulls a lever, a sophisticated sear and release system, involving a rotating nut that holds the drawn bowstring, disengages, unleashing the stored energy of the prod with terrifying force. The key innovation is that this entire process is contained within a single, self-contained unit that can be mass-produced and easily replaced. The true genius of this mechanism is revealed not in its use, but in its manufacture. Qin artisans achieved something that would not become standard in the West until the Industrial Revolution: full interchangeability of parts. Archaeologists excavating the terracotta army pits have recovered thousands of these bronze triggers. When they are examined, an astonishing fact emerges. The individual components, the lever, the sears, the housing box, are so precisely cast and finished that apart from one crossbow can be swapped with the same part from any other crossbow, and the mechanism will still function flawlessly. This was not accidental. It was the result of a deliberate, state-driven manufacturing system. The Qin regime established official workshops with strict quality control. Artisans used standardized molds, likely made from master patterns, to cast the bronze parts. After casting, the parts were likely finished using jigs or fixtures that ensured every surface was filed to an identical dimension. This meant that a Qin armorer in the field, facing a broken crossbow, didn't need a skilled blacksmith to painstakingly craft a unique replacement part. He could simply open a crate of standardized spares and swap in a new trigger mechanism in minutes, getting a vital weapon back into the fight with incredible speed. This approach to production represents a fundamental shift in thinking. It's the birth of the assembly line concept, centuries before Henry Ford. The Qin understood that to equip a massive, campaign-hardened army, they couldn't rely on individual craftsmen making unique items one at a time. They needed a system that could output vast quantities of highly complex, yet perfectly identical, objects. By breaking down the trigger mechanism into its component parts and standardizing each one, they could assign different workshops or even different laborers to specialize in producing just one type of part. This division of labor increased efficiency and output exponentially. It also ensured a consistent, high level of quality across the entire army. Every Qin crossbowman, from the front lines to the furthest garrison, wielded a weapon of identical power and reliability. This logistical and tactical advantage was overwhelming. The crossbow itself transformed the nature of warfare in ancient China. It was the great equalizer. Training a skilled archer capable of drawing a powerful composite bow accurately required years of practice and immense upper body strength. In contrast, a crossbow could be mastered in a matter of weeks. A soldier simply had to place his feet in a stirrup at the front of the weapon, use the strength of his legs and back to draw the string back to the trigger latch, a technique far more powerful than using just arm strength, aim, and fire. This meant that the Qin could conscript vast numbers of peasants and quickly turn them into highly effective soldiers capable of punching through the armor of the most elite enemy warrior. The crossbow allowed for new, devastating tactics. Qin formations could unleash volleys of bolts with shattering force, breaking cavalry charges and decimating infantry lines long before they could close for hand-to-hand combat. The standardized trigger was the heart of this system, the component that made such large-scale, coordinated fire possible. It was a weapon that valued systemized production and disciplined drill over individual heroic prowess, a philosophy that perfectly mirrored the legalist, centrally controlled state of Qin Shi Huang. The success of this technology is etched into history. It was a key factor that allowed the Qin to defeat 6 rival warring states and forge a unified China, creating an imperial template that would last for 2 millennia. The humble bronze trigger, a triumph of precision and standardization, truly was the machine part that built an empire. Stepping away from the mechanical genius of gears and triggers, we now venture into the realm of pure intellect, where ancient minds sought to map the very fabric of time itself. While the Romans were building aqueducts and the Chinese were forging iron, on the other side of the world, in the lush rainforests of Mesoamerica, the Maya civilization was achieving a conceptual breakthrough so profound it still inspires awe today. They weren't just tracking days and seasons. They were constructing a complex, multi-layered calendar system of breathtaking mathematical elegance and astronomical precision, a system that viewed time not as a simple line, but as a series of interlocking, sacred cycles. At the heart of this system was the famous long count calendar, a tool for measuring epochs so vast it reveals a Maya conception of time that was, in many ways, more sophisticated than anything found in the Old World. To understand the long count, we must first appreciate the Mayas' unique relationship with time. For them, time was not a neutral, abstract progression. It was a divine force, animated by the gods, and each day carried its own spiritual weight and destiny. Their calendar system reflected this by weaving together several separate cycles. The 2 most important were the 260-day sacred round, known as the Tzolk'in, and the 365-day vague year, or Hob. The Tzolk'in was a combination of 13 numbers and 20-day names, while the Hob consisted of 18 months of 20 days each, plus a short, 5-day period considered unlucky. But the real engine for measuring long stretches of history was the long count. Think of it as a cosmic odometer. Instead of counting in base 10 like we do, the Maya used a base 20, or vigesimal, system, with one critical modification for tracking time. The long count date was expressed as a series of 5 components, each representing a different order of magnitude. Starting from the smallest, there was the kn, a single day. 20 kns made a winnel, or month. 18 winnels, however, made a ton, a year of 360 days. This is the key modification, using 18 instead of 20 to make the ton align roughly with the solar year. From there, the count returned to base 20. 20 tons made a katon, about 20 years. 20 katons made a bakton, a period of roughly 394 years. A complete long count cycle, from the mythical starting point of the current creation, consisted of 13 baktons. This is the cycle that generated so much global attention leading up to the year 2012, which simply marked the completion of one 13 bakton cycle and the beginning of the next, not an apocalyptic end. The ability to pinpoint any single day within a span of over 5,000 years with such a consistent, place value notation was a staggering intellectual feat. This system was impossible without one of the Maya's greatest gifts to mathematics, the concept of zero. Long before the idea appeared in India and traveled to Europe, Maya scribes were using a shell symbol to represent a true placeholder zero in their complex calendrical calculations. This wasn't just an empty space, it was a number in its own right, essential for their place value notation. A date like 9 baktons, 12 katons, 4 tons, 0 winnels, and 15 kns could be written clearly and unambiguously. The zero allowed them to perform the advanced arithmetic needed to project their calendars far into the past and future, to calculate the anniversaries of royal accessions, and to predict celestial events with pinpoint accuracy. The sophistication of this mathematical framework, developed in isolation from the rest of the world, stands as a lonely beacon of abstract thought. Their astronomical observations were the bedrock upon which this precise calendar was built. From observatories like the Karakol at Chichen Itza, Maya astronomer priests meticulously charted the movements of the sun, moon, and planets over centuries. They calculated the solar year to be 365.2420 days, and figure even more accurate than the Julian calendar used in Europe at the time. They tracked the complex cycles of Venus, which they associated with war, creating a 584-day Venus calendar that was accurate to just a few hours over a span of centuries. Most impressively, they understood the Saros cycle, the approximately 18-year period after which the Sun, Moon, and Earth return to the same relative geometry, allowing them to predict solar and lunar eclipses. These were not wild guesses. They were the result of generations of meticulous record-keeping, a legacy of data inscribed in thousands of hieroglyphic texts on stone stelae and bark paper codices. When we compare the Maya calendar system to those of contemporary Europe around the 8th or 9th century, the contrast is striking. Europe was using the Julian calendar, which had drifted significantly from the solar year, leading to confusion about the dates of religious festivals like Easter. The concept of zero was unknown, and complex astronomical prediction was largely the domain of a few isolated scholars. The Maya, meanwhile, had integrated their calendar into every facet of life, from agriculture to religion to politics. A king's accession was timed to propitious dates in the cycle, and major monuments were erected to mark the completion of important kaetons. Their system was a holistic fusion of science, mathematics, and spirituality, a grand intellectual architecture designed to harmonize human activity with the perceived rhythms of the cosmos. It represents a pinnacle of human thought, a testament to the power of the human mind to find order and meaning in the vast, inexorable flow of time. But even the most brilliant minds of the Maya, tracking the cycles of the heavens, were ultimately bound by the most fundamental earthly need, the relentless, life-sustaining necessity of fresh water. This was a challenge faced with particular urgency in one of the world's most formidable landscapes. Imagine the vast, sun-scorched plateaus of ancient Persia, a land where rain was a rare blessing and survival depended on a desperate ingenuity. Here, in this arid crucible, Engineers perfected one of the most sustainable and impactful water management systems ever devised, a subterranean masterpiece known as the Canat. This was not merely a tunnel, it was a civilization's lifeline, an underground river summoned by human will to defy the desert itself. The principle of the Canat is one of elegant simplicity, but its execution was a feat of breathtaking daring and precision. The process began high in the foothills of mountains, where snowfall and rare rainfall would percolate through the soil to form underground aquifers. Persian hydrologists, with an almost intuitive understanding of geology, would identify a location where the water table was accessible. There, they would dig a vertical shaft, often over 100 feet deep, straight down to the water. This mother well was just the starting point. From its base, a team of skilled diggers, known as mucanis, would begin the Herculean task of excavating a gently sloping tunnel, heading miles across the desert toward the location of a city or an agricultural oasis. This is where the true genius of the Canat reveals itself. The slope of the tunnel, or kares, had to be meticulously calculated. It needed to be just steep enough to allow water to flow by gravity alone, yet shallow enough to prevent erosion that would collapse the tunnel or cause the water to flow so fast it would surge out at the destination. There were no laser levels or GPS for these ancient surveyors. They used simple, yet remarkably effective, tools like water-filled bowls to ensure a level gradient or weighted strings to measure the precise angle of descent over vast distances. As the horizontal tunnel extended, the crew behind them would dig a series of additional vertical shafts from the surface down to the tunnel's level, spaced about every 60 to 100 feet. These shafts served a dual purpose. They provided ventilation for the diggers working deep underground, and just as crucially, they provided access for the monumental task of removing the excavated earth and rock. The line of these vertical access shafts, visible as a series of craters marching across the desert landscape, became the unmistakable signature of a Canat system. The advantages of this underground aqueduct were profound. By transporting water in a sealed tunnel, the Persians solved the two great problems of desert water supply: contamination and evaporation. The water, protected from the scorching sun and blowing sand, remained clean and cool. There was no loss to the atmosphere, making the Canat incredibly efficient. At its terminus, the water would emerge into a sunlight surface canal or a collection pool, a jub, from which it would be distributed to fields and homes. The flow was constant and reliable, a steady, life-giving pulse that was measured and allocated through a sophisticated system of water rights, often managed by a local water master. This wasn't just a piece of engineering, it was the foundation of social order and economic prosperity. The impact of the Canat technology cannot be overstated. It allowed cities like Persepolis to flourish in regions that would otherwise have been incapable of supporting a large, settled population. Vast stretches of desert were transformed into lush gardens and productive farmland, creating the fabled Persian gardens that became symbols of paradise. This technology did not remain a Persian secret. It spread along the Silk Road, carried by traders and conquerors. Variations of the Canat appeared across the ancient world, from the Middle East to North Africa, and even as far as Spain, where they are known as acequias. Some of the oldest Canats, dating back 3,000 years, are still in use today in Iran, a testament to their enduring, sustainable design. In a modern world grappling with water scarcity, these ancient tunnels offer a powerful lesson. They represent a philosophy of working in harmony with the environment, of tapping a resource without depleting it, and of building infrastructure not for a generation, but for millennia. The Canat is a silent, flowing monument to the foresight of its creators, a reminder that the most advanced technology is often the one that sustains life most gently and effectively. Hero's whirling sphere of steam presents us with perhaps the most poignant what-if in the entire history of technology. We have a working model of a fundamental principle, the conversion of heat into motion, sitting right there in 1st century Alexandria. The intellectual spark was struck, so why did that spark fail to ignite the tinder and blaze into an ancient industrial revolution? The answer is not a simple one. It's a complex tapestry woven from the very fabric of ancient society. revealing that a great invention is never enough on its own. It must land in a world that is economically, socially, and culturally ready to receive it. The most immediate and powerful barrier was economic. The Roman economy, the context in which Hero demonstrated his device, was fundamentally built on a foundation of abundant and cheap labor in the form of slavery and widespread indentured servitude. For a wealthy landowner, or the state itself, the calculus was brutally straightforward. Why invest a fortune in developing an unproven, complex steam engine to power a mill, a mine, or a pump, when human muscle power was readily available and required only the cost of basic sustenance? The initial research and development, the precision engineering of high-pressure boilers that wouldn't explode, the creation of a network to supply fuel, these were monumental, risky investments. The economic incentive to mechanize simply didn't exist when the alternative was so inexpensive and required no technological infrastructure. Innovation thrives on necessity, and in a world saturated with manual labor, the necessity for steam power was virtually non-existent. Beyond the economic calculation lay a profound cultural and philosophical disconnect. The ancient mindset toward machines like the Eolipile was fundamentally different from our modern drive for productivity. For thinkers like Hero, such devices were often classified as thaumato wonders or marvels. They were created to illustrate philosophical principles about the nature of air and motion, to inspire awe in temple courtyards, or to simply demonstrate the inventor's cleverness. They were toys for the intellectual elite, fascinating curiosities rather than tools for transforming production. The concept of technological progress as an endless, linear march toward greater efficiency and material abundance is largely a modern construct. The ancient world valued stability, tradition, and philosophical contemplation. A device that could automate work was not seen as a way to liberate humanity from toil, but perhaps as a threat to the natural social order or, at best, as a neat trick with no practical application to the serious business of farming, building, or governing. This points to a third critical factor, the lack of integration between theoretical science and practical technology. While the Greeks, particularly in Alexandria, had made staggering advances in mathematics, geometry, and even basic physics, this knowledge often remained within the walls of the library. It was the domain of philosophers, not engineers. The craftsmen who built things, the blacksmiths, the millwrights, the shipbuilders operated within a tradition of passed-down, empirical knowledge. There was no feedback loop where a theoretical understanding of thermodynamics could inform the practical design of a more efficient engine, or where the challenges faced by a mine owner trying to drain water could be presented to a community of scientists for a systematic solution. The Eolipile was a brilliant idea that remained an island, disconnected from the mainland of practical need and from the other branches of knowledge that would have been necessary to scale it up. Imagine for a moment an alternate history where these barriers had fallen. Suppose a Roman administrator, frustrated by the cost and inefficiency of using teams of slaves to operate a massive water lifting wheel in a deep mine, had seen the potential in Hero's device. He commissions a team to develop a larger, more powerful steam engine to drive a pump. This effort would have immediately run into a wall of technological limitations. The metallurgy to safely contain high-pressure steam did not exist. The precision engineering required for pistons, cylinders, and valves that could maintain a tight seal under continuous stress was beyond the capabilities of ancient workshops. Even the mathematics needed to calculate stress loads and power output was in its infancy. The steam engine was not a single invention, it was a cascade of interconnected innovations. The Eolipile was the first brilliant drop, but the ancient world lacked the conditions for that drop to create a ripple effect. It was a potential path that required 1,000 other discoveries, a different social structure, and a new way of thinking about the world itself. The silence that followed Hero's demonstration is a haunting reminder that progress is not inevitable. It is a fragile dance between human ingenuity and the specific historical moment that either nurtures it or lets it vanish into the air, like steam from a forgotten toy. The enduring mystery of the Baghdad Battery is not just a question for historians. It has become a compelling challenge for experimental archaeologists. These modern-day investigators use hands-on experimentation to test historical hypotheses, and they have taken the simple components of the clay jar, the iron rod, and the copper cylinder into the laboratory to see if the theory holds a practical charge. The results are both definitive and thought-provoking. When a replica of the jar is filled with an acidic electrolyte, something as common as vinegar or grape juice, both readily available in antiquity, a measurable electric current is indeed produced. The voltage is low, typically generating only around 1 volt, but by connecting several of these jars together in a series, as one might with modern batteries to power a small device, the voltage can be increased. This simple experiment proves that the object's physical form is, without a doubt, functionally capable of being a primitive galvanic cell. This demonstration of possibility naturally leads to the most captivating application, electroplating. Imagine an ancient artisan's workshop, perhaps in a bustling Parthian market. This craftsman specializes in creating religious amulets or decorative jewelry, taking objects made of silver or copper and giving them the appearance of solid gold. The traditional method, fire gilding, involved mixing gold with mercury, applying it to the object, and then heating it to vaporize the mercury, leaving behind a gold coating. This process was not only dangerous due to the toxic mercury fumes, but also difficult to control, often resulting in an uneven finish. Now, picture an alternative method. The artisan prepares a solution containing gold salts, perhaps made by dissolving gold in a mixture of acids like vinegar and saltpeter, a chemical process that was within the realm of ancient alchemical knowledge. He then suspends the silver object in this solution and connects it with a wire to the copper cylinder of one of his clay jar batteries. The iron rod is connected to a small piece of pure gold. When the circuit is completed, a fascinating transformation begins. Over the course of several hours, atoms of gold from the solution are gradually deposited onto the surface of the silver object, creating a thin, incredibly smooth, and perfectly even layer. The result is a gilded object of exceptional quality, its luminous finish appearing almost magical to a culture with no concept of electricity. This electroplating hypothesis provides a compelling and elegant explanation for the existence of certain ancient gilded artifacts that exhibit a fineness and uniformity difficult to achieve with other known techniques. Yet, even if we accept that the Baghdad jars were indeed ancient batteries, we are faced with an equally puzzling question. Why did the technology not develop further? The answer lies in the profound gap between having a tool and understanding the science behind it. The ancient users of such a device would have had no concept of electrons, current, or electrical theory. To them, the effect would have been a form of chemistry, or perhaps even alchemy, a useful, repeatable phenomenon without a deeper explanatory framework. Without that fundamental understanding of why it worked, there was no foundation upon which to build. There was no next logical step, no impetus to scale up the technology for larger applications like lighting or motive power. A single volt is enough for subtle electroplating, but it is useless for anything requiring significant energy. Furthermore, the practical applications in the ancient world were incredibly limited. What need was there for a steady, low-level electric current? There were no electric lights, no motors, no telegraphs. The sole plausible use, electroplating, was a niche artisanal technique. For the vast majority of society, from farmers and soldiers to bureaucrats and rulers, this subtle trickle of electricity would have had no perceivable value. In an economy driven by agriculture, construction, and warfare, investment and innovation flowed toward technologies that offered clear, large-scale advantages: better irrigation, stronger metallurgy, more effective siege engines. A technology that produced a faint tingling sensation or a slow chemical transformation simply could not compete. It was a solution in search of a problem, a seed of potential that fell on stony ground because the social and economic conditions needed to nurture it were a millennium away. The Baghdad Battery, therefore, remains a tantalizing enigma. It represents either a brilliant, isolated accident of proto-science that was never understood well enough to flourish, or a simple storage jar that we, with our modern knowledge, cannot help but see through an electrical lens. In either case, It challenges our linear view of progress, reminding us that the path of invention is filled with forgotten branches and possibilities that were simply ahead of their time. Yet behind every gear in the Antikythera mechanism, every self-healing property of Roman concrete, and every precise calculation of a Maya calendar, lies an invisible foundation, the pure, abstract language of mathematics. It was this mastery of numbers, shapes, and patterns that provided the essential toolkit for ancient engineers, a theoretical framework that allowed them to translate visionary ideas into tangible reality. The connection between a mathematical equation scribbled on papyrus and an aqueduct spanning a valley was direct and profound. It was the difference between guesswork and genius. Our story begins not with numbers, but with shapes, in the sun-drenched agora of ancient Greece. Here, thinkers like Euclid of Alexandria were systematically organizing the principles of geometry into a coherent logical structure. His monumental work, The Elements, is arguably the most influential textbook ever written, but its genius was not in the discovery of new theorems alone. It was in the method. Euclid started with a handful of self-evident truths, or axioms such as the fact that a straight line can be drawn between any 2 points, and from these simple beginnings, he built an entire edifice of geometric proof, step by logical step. This was the birth of deductive reasoning, the powerful idea that complex truths about the world could be derived from a few fundamental principles. For an engineer, this was revolutionary. It meant that the stability of a triangular truss in a bridge wasn't just an observed phenomenon, it was a mathematical certainty. The geometry of a right-angled triangle, explored in the Pythagorean theorem, allowed for precise land surveying and the construction of perfectly square foundations for temples and cities. Greek geometry was the ultimate engineering software, providing the rules to ensure that their magnificent structures wouldn't just stand, but would stand with perfect, predictable integrity for millennia. While the Greeks were perfecting the geometry of the physical world, a mathematical revolution of a different kind was unfolding in India. Here, mathematicians were grappling with the concepts of the infinite and the void, leading to one of the most pivotal intellectual breakthroughs in human history, the invention of the number zero. For centuries, ancient number systems like the Roman numerals had been clunky and inefficient for calculation, lacking a placeholder to indicate an empty column. The Indian concept of sunya, meaning void or empty, transformed mathematics. By the 7th century, mathematicians like Brahmagupta were not only using a symbol for zero, but had also established formal rules for arithmetic with it, including the daring idea that a number divided by zero is undefined. This was more than a notational convenience, it was the key that unlocked the modern place-value number system, making complex multiplication, division, and algebra vastly simpler. This system, which we now call Hindu-Arabic numerals, would eventually travel to the West and become the foundation of all modern science and commerce. But the Indian mathematical imagination soared even higher. In the Kerala school of mathematics, centuries before Isaac Newton and Gottfried Leibniz in Europe, scholars like Madhava of Sangamagrama were developing astonishingly sophisticated ideas that foreshadowed calculus. They derived infinite series for trigonometric functions like sine and cosine, and even formulated a series for pi that converges rapidly, allowing them to calculate its value to 11 decimal places. Most strikingly, they developed concepts of differentiation and integration, using them to solve problems in astronomy related to the instantaneous motion of the planets. This was not yet the full, generalized calculus of Newton, but it was a monumental leap towards understanding continuous change. These discoveries remained largely confined to southern India, a breathtaking example of a parallel intellectual path that was tragically isolated from the broader scientific conversation. Long before either the Greeks or the Indians, however, the pragmatic merchants and astronomers of ancient Babylon had already developed a highly advanced form of algebra. Theirs was a society built on commerce and administration, and their mathematics reflected this practical need. Using a base 60, or sexagesimal, system, which is why we still have 60 seconds in a minute and 60 minutes in an hour, they performed complex calculations on clay tablets. These tablets are filled with sophisticated problems that we would recognize as quadratic and even cubic equations. They had algorithms for calculating compound interest, for dividing inheritances, and for determining the dimensions of fields. One of their most famous achievements, the clay tablet known as Plimpton 322, contains a table of Pythagorean triples, sets of three whole numbers that satisfy the relationship a 2 plus b 2 equals c2 for a right triangle. This suggests they understood the principle behind the Pythagorean theorem over 1,000 years before Pythagoras himself was born. Babylonian math was not primarily about abstract proof. It was a tool for solving real-world problems of trade, land management, and celestial prediction, demonstrating that the drive to quantify and calculate is one of the oldest engines of civilization. The true power of this ancient mathematical genius is revealed precisely at the points where theory and practice converge. The Antikythera Mechanism is the ultimate example. Its intricate gear trains are a physical manifestation of deep astronomical cycles, ratios, and prime number theory. The Indian concept of zero was essential for the Mayas' ability to compute their long count calendar over spans of thousands of years. The Roman surveyors who laid out their arrow-straight roads and aqueducts did so using the geometric principles formalized by the Greeks. This was not a one-way street. Practical challenges, like the need to predict the Nile's flood or to calculate the volume of a grain silo, constantly fed new problems back to the theoreticians, pushing the boundaries of abstract thought. This virtuous cycle between the quest for pure understanding and the demands of applied engineering is what truly set these civilizations apart. They demonstrate that the most enduring inventions are never merely clever gadgets. They are the children of a profound and fearless curiosity about the invisible rules that govern our universe, a curiosity expressed in the timeless, universal language of mathematics. This recurring theme of breathtaking advancement followed by profound loss forces us to confront a disturbing pattern in human history. Technological regression is not the exception, but a terrifyingly common occurrence. The spark of genius that illuminated the Antikythera Mechanism, the secret alchemy of Greek fire, the self-healing wisdom of Roman concrete, these were not simply misplaced. They were systematically extinguished by the very tides of history that swept away the civilizations that nurtured them. The primary engines of this forgetting are tragically familiar: the cataclysm of war, the slow collapse of sprawling empires, and the deliberate or accidental destruction of the great repositories of knowledge. War is the most brutal and immediate eraser. The fall of a city often meant the slaughter or enslavement of its most skilled artisans and engineers. The intricate knowledge required to craft a differential gear or to mix a volatile chemical weapon dyes with the masters who held it. But even more devastating than a single battle is the collapse of an entire imperial system. The Roman Empire did not vanish in a day. It frayed at the edges over centuries. As its borders contracted and its economy faltered, the complex infrastructure that supported advanced technology disintegrated. The state-sponsored workshops that produced standardized crossbow triggers or maintained aqueducts ceased to exist. The long-distance trade routes that supplied special ingredients like pozzolana ash were severed. Specialized knowledge, no longer in demand and without a patron to support it, simply faded from memory, becoming the stuff of legend told by people who could no longer replicate the wonders they described. Perhaps the most poignant symbol of this loss is the Great Library of Alexandria. More than just a building filled with scrolls, it was the intellectual heart of the Hellenistic world, a center where scholars like Archimedes, Eratosthenes, and Hero could share ideas and build upon each other's work. It represented the very principle of cumulative knowledge. The series of fires that ultimately destroyed the library, whether started by Julius Caesar, Christian mobs, or later conquerors, did more than burn papyrus. They severed a vital thread of intellectual continuity. The collective understanding of mechanics, astronomy, and engineering that was concentrated in that one place was scattered to the winds and irreparably damaged. With it died the potential for a technological trajectory that integrated the steam engine with precision gearing, a path that might have altered the course of human history. This stands in stark contrast to our modern paradigm. Since the scientific revolution and the invention of the printing press, our model has been overwhelmingly cumulative. A discovery published in a scientific journal in Japan can be read, tested, and built upon by researchers in Germany or Brazil within days. Knowledge is now stored in a distributed, redundant network of digital and physical archives, making it incredibly resilient to localized disaster. We assume progress is a one-way street, that our understanding will only deepen, but the lesson of antiquity is a humbling corrective to this assumption. It shows us that progress is fragile, a delicate flame that requires a stable, supportive society to keep it burning. Without that, darkness can return with startling speed. This realization invites a thrilling, almost dizzying possibility. If we have rediscovered just a handful of these ancient marvels by chance, a mechanism found in a shipwreck, a lens uncovered in a palace ruin, what other secrets remain buried? The archaeological record is infinitesimally small compared to the vast span of human history. For every Antikythera mechanism that survives, how many thousands of equally complex devices have corroded to dust? The stories that have come down to us, of automatons and flying machines, were long dismissed as pure myth. But now, knowing what we know, we must look at these legends with new eyes. Were they merely fanciful stories, or were they garbled accounts of real technological achievements, their principles lost to time? The silent, stoic endurance of the Iron Pillar of Delhi and the Pantheon's dome are permanent challenges to our arrogance, suggesting that ancient ingenuity may have reached heights we are only beginning to glimpse. They are not primitive precursors to our modern world. They are potential alternate paths, lonely monuments to a brilliance that was, and a haunting reminder of how much can be forgotten. From the microscopic dance of gold nanoparticles in a Roman cup to the grand cosmic calculations of a Greek gearwork computer, the journey we have taken together is nothing short of mind-boggling. We have witnessed steel that could bend without breaking, concrete that could heal its own wounds, and cities that mastered public health millennia before the advent of modern medicine. Each of these 30 inventions is a monument to a singular, brilliant flash of human ingenuity, a testament to the fact that the drive to innovate, to understand, and to improve our world is a fundamental part of the human spirit, as present 2,000 years ago as it is today. Yet, the most profound lesson these artifacts teach us is not about continuous advancement, but about profound loss. They reveal a history that is not a smooth, upward slope of progress, but a landscape of jagged peaks and deep valleys. Time and again, we see civilizations scaling incredible heights of technological and scientific understanding, only to have that knowledge vanish, sometimes in the smoke of a burning library, sometimes in the quiet fading of a specialized craft, sometimes for reasons we may never fully comprehend. The Antikythera Mechanism was not an evolutionary step toward the modern computer. It was a lonely pinnacle, an isolated island of genius in a sea of forgotten potential. The same spark of genius that illuminated Hero's workshop had to be painfully rekindled more than 1,000 years later. This recurring pattern forces us to abandon the comfortable, linear narrative of history we so often take for granted. It challenges our modern arrogance, our assumption that we stand alone at the summit of human achievement. The truth is far more humbling and far more fascinating. We are not the first to dream of mechanical wonders or to unlock the secrets of materials. We are simply the latest in a long line of curious beings, standing on the shoulders of giants whose names we have forgotten and whose works we are only just beginning to rediscover. So I leave you with this final thought. The next time you walk through a museum or gaze upon an ancient ruin, try to see it with fresh eyes. Look past the silent stones and the faded artifacts, and see the vibrant, intellectually daring cultures that created them. Question the simple story of progress. Wonder about the roads not taken, the technologies lost to time, and the echoes of brilliance that still whisper to us from the distant past. History is not a closed book. It is a living, breathing mystery, filled with secrets waiting to be uncovered. Now, I am incredibly curious to hear from you. After this journey through lost marvels, which of these ancient inventions leaves you the most astonished? Was it the intricate mechanics of the Antikythera device, the sheer durability of the Iron Pillar, or something else entirely? Share your thoughts in the comments below. Let's continue this exploration together.